Hello, and welcome to the Coopersmith Career Consulting Crash Course video for IT-120, an introduction to computing and program design. In this video, we will be covering the core material in the course, which provides a broad introduction to the use of computers for such things as creative endeavors, communications, organizing information, and problem solving. We will be discussing the basic components of computer hardware, software, networking, and the internet in context of the current state, trends, and challenges of various aspects of computing such as computer hardware and software, and programming languages. This crash course video will hopefully prepare you to take your final exam. The final exam will be drawn from a large test bank, and you will have 3 hours to complete it. Please reference your syllabus for the detailed information. Here are the major course topics which will be covered. This is also published in your syllabus, and you will see that we will go through each one in detail in this video. The goal of this course is to enhance your knowledge of the fundamental concepts of computer science and basic computer architecture terminology. We're going to increase your understanding of the elements of social, legal, and ethical issues as they pertain to computer usage. We want to provide you with the hands-on experience using the internet to do research and to extend your knowledge of computer-related vocabulary and understanding of problem-solving skills. At the end of the course, you should be able to have the learning outcomes listed here. The textbook for this course is by Lawrence Schneider, and it's called Fluency with Information Technology. This is the 6th edition that is copyrighted 2015. So let's get started. First of all, computers are everywhere. They're in laptops, tablets, smartphones, and things as simple as anti-lock brakes and TV remotes. In 2010, over 24 billion of these devices were shipped, which means that every consumer in the developed world owns over a dozen of these devices. Now, computers don't always have to have a keyboard and a printer attached, but they do have metal plates that will shield them from the electromagnetic radiation. What we want to talk about are the two major components of computers, and computing in its most general form concerns data, hardware, and software. Now, hardware is the physical embodiment of computation. It's basically a representation of one of the greatest technological achievements of the last decade. Very few inventions are more important. On the software side, what they do is instruct the computers with the steps they need to implement the applications. And unrestricted by the physical world, it can direct a computer to do almost anything. So let's talk a little bit more about software. It's a collective term for programs, and programs are the instructions that computers perform to implement their applications. So basically, the software will instruct the computer, which is the hardware, by providing the steps needed to perform a task. The computer will then follow the program and carry out the instructions. So this is known as the software stack. This is the concept that we use to structure and organize the software in a contemporary computer system. It's going to be a series of layers of programs that implement the user applications, and each layer will implement operations used to build the layers above. Now, writing software is difficult and challenging. What it does is instruct the agent to perform some function or action by giving that step-by-step process. The agent is considered anything that can follow these instructions. So for software professionals, the agent is a computer. So let's see what this software stack looks like visually in an example. So we want to check out a video on YouTube using our smartphone. How would this happen? Well, as you can see, the smartphone hardware is down here at the very bottom layer, and then as we increase in complexity, we go through the different software stack layers. So the first thing we would do is open the browser application to get to YouTube. Then the browser app will use the Windows Manager and other frameworks. The Windows Manager will use the Media Manager and several other libraries. And then the Media Manager will use your display driver and several other kernel operations. So let's talk about the distinguishing factor of data. As we said before, in the basic, most simplest terms, computing is data, hardware, and software. Now, data is sometimes interchanged with information, like it's no different concept in computing. However, there are some significant differences that we will get into later in this video. In its physical form, information is literally everywhere in the physical world. It can be captured and converted into the digital form, and it's always represented as bits, which are zeros and ones. Now, what kind of information do we use? Most of the information we use is delivered by the World Wide Web. Newspapers, TVs, magazines, libraries deliver information, but in a diminishing role compared to the web. Some digital data, like GPS or ATM transactions, is not delivered by the web at all. So let's speak a little bit about the right computing terms, because without understanding a little bit of the jargon, you can't really understand how you can benefit from this technology. So we're going to talk about why we want to learn some of these terms. First of all, if you're calling tech support, everybody needs it and uses it, and so we need to be able to communicate what our problems are clearly and accurately. Also, to learn a new subject, we have to learn the terminology involved. So let's talk a little bit about tech support. Usually we can look up the answer ourselves using the help feature, or you have to contact tech support to do more elevated actions. The technician might not know exactly what we're talking about, and without the right word, the search algorithm of the help facility really won't work very well for you. So let's talk about algorithms. It's a precise symptomatic method for producing a specified result. We use and invent algorithms all the time to solve our problems, and the agent or the computer that runs the algorithm is usually a person. Now, computers are clueless. They need to be told what to do. They follow a very specific set of instructions to give you an outcome. Now, for the method to be precise enough for a computer to follow, everything needs to be spelled out. So programmers have to make algorithms that are perfectly precise for computers by writing them in what we call a programming language. Now, the difference between computers and people is that we do have a clue. So many things can be left out of an explanation where people have to follow directions that cannot be left out when you're writing programs. So algorithms are a precise symptomatic method for producing a specified result, whereas programs are algorithms that have been specialized to a specific set of conditions and assumptions and are usually written in a specific programming language. In most cases, however, we can use these terms interchangeably. So let's talk about some of the words that we use for ideas. Abstract. In computing, to abstract means to remove, but this time it's an idea or a process and it's extracted from some form of information. So abstractions are parables and fables, which require us to abstract the essential point of the story so that we can learn from it. There's two key points here. Many, but not all of the details of the story are relevant to the concept, and the abstraction has to have a meaning beyond the story. So in computing, separating the relevant from the irrelevant and applying the abstraction to the other cases is essential. Generalize is the process to recognize the common idea in two or more situations. And to generalize is to express an idea or concept that applies to very many situations. And the statement that sums up the idea is called a generalization. If it is true most of the time, we can generalize an idea. Operationally attuned is the ability to apply what we know about how a device or system works to simplify its use. Some examples of this is, for instance, we loosen lids by turning it to the left and then tighten it by turning it to the right. We know this intuitively, but knowing it explicitly will make you operationally attuned. Mnemonics are an aid for remembering something. So these are when you have things like homes, which is the Great Lakes, Huron, Ontario, Michigan, Erie, and Superior. Or some kind of sentence like Mary's violet eyes make John stay up nights, which is a way for remembering all of the different planets. With computing, think about how computation works, makes it simpler to use. So feedback is a very important concept in computing. Basically, a computer is just our assistant. It's going to do whatever we ask it to do. But we want our assistant to be able to report on the progress of the task that it's doing. We need to know that the task was done and when to give it another one, or if there was some kind of problem completing the task. So computer systems always give the user feedback about what is happening. It's an indication that either the computer is still working on it or that it is done, and it can take many forms. The revision is either visible or areas on the screen become highlighted, shaded, gray, underlined, color change, or you might even hear an audible sound like a click. Now, the most common form of feedback in computing is that the computer is going to be performing a time-consuming operation. You have some indications of that down here below, but the cursor will often be replaced by a different icon. Now, some applications will give customized feedback or use some kind of a progress bar to give you an estimate on the time remaining. However, in computing, you should always be able to expect that feedback. Now, having a consistent interface is also a principle of design. Now, what we are looking at here is regardless of who makes the software, any kind of icons or menus should be similar. And this is especially so within a specific company. Microsoft, for example, all the Microsoft products have similar features and design. We have similar menus like File and Edit and similar functions within those menus like cut, copy, and paste in the Edit menu. Now, the reason we do this is because companies reuse the same code in a lot of their applications to save on a lot of time-consuming parts of the application. But also from the user perspective, it really aids you in learning and using the additional products that they put out, because certain operations are so fundamental to processing that it's intuitive almost on how to use those operations in the application. So let's look at like creating a new instance of something. Under the File menu, you can usually find a command called New. That's going to create a blank instance of the kind of files that the application creates. So what do we consider blank information? It's basically a record, and it's an empty structure that will hold the properties of that file and store its content. So what we have here is an example of an address book entry where it can hold names, images, and phone numbers about the new individual that we want to save into our contact book. So designers use this consistency as well to provide a strong sense of familiarity with their new applications. So when a user gets a new application, they do two things. They click around to explore the application and see what features are available, and they do what's called blazing away, which is trying the application in a way that they haven't done so before. Now, computers encode information as a sequence of binary digits, which are zeros and ones, and because of the use of these two digits is why we call it digital information. Now, by using only those zeros and ones, we can take that digital information and perfectly reproduce it or replicate it. So second copy can be made by simply duplicating the sequence of zeros and ones. And this is one way that digital improves upon analog information, because analog information will come from a continuously variable medium, such as a piece of paper that will crinkle and change color over time. So when you make a copy of that image, for example, it could come out too dark or too light when compared to the original. And one of the problems with this is that every copy that you make will degrade in quality. But with digital information, a perfect reproduction can be made. It doesn't matter where the copy came from. Both the original and the copy are going to be the exact same sequence of ones and zeros. So every copy can be made from the last copy and it will still be identical to the original and have the same quality. So three operations that you're probably familiar with is the copy, paste, and edit operations. These are available in a lot of different applications, and when editing a file, you can either create content from scratch or use copy and paste to reproduce it from another location. It's generally faster and less error-prone. So how do we learn from technology? Well, when using a find and replace editing operation, the source content to find is identified in the document. Then the target content to replace is also identified. Now, what it will do is it will take that in turn and just swap it out with whatever you want to replace it with. Now, find and replace all is an all-at-once version of copy and paste. And it's basically an abbreviation of a long name or title as a placeholder, and then you can use the find replace all to put the correct name in all at once. There's many placeholder techniques that we can use when the purpose or operation of a new technology may seem obvious. Some technologies will require instruction, like driving a car using a chainsaw, for instance, but a lot of the technology that we use today, we figure out on our own. We know kind of intuitively what to do with it, and the technology developers do that on purpose. So in computing, a metaphor is an icon or an image that is used as a representation, or it's symbolic of something that we have to do in computation. So when designers created technology, they used the metaphors to help users know how to operate their devices without reading a manual. So metaphors are a terrific solution. So let's hear a little bit about what our author says about the use of metaphors in computing.
A metaphor is basically a crutch to explain to a new user some concept that we're trying to present on the screen, some concept in user interface, to help them understand how to use this new interface component to get their work done. One of the reasons why we have metaphor is it's based in this notion of having a direct manipulation user interface. The concept of a direct manipulation user interface is that what you see on the screen is what you manipulate, what you move, change, or somehow modify. One of the things that you see as a common metaphor in computing is this notion of a computer desktop. What we try and do is simulate your physical desk on the screen. And so we have a whole set of artifacts, like the window to look into or peer through a document. We have things like a trash can to tell you how to throw things away. We have things like file folders that you open or close to be able to look in and see what's stored in there. One of the ideas behind using metaphor is that when you see a metaphor on a computer screen, you'll get the idea of how you might use it in practice. So if you see something like a lock or a key on the screen, that what you'll understand is that that's somehow providing some notion of security, that you're trying to lock something up or you're trying to unlock it if you're using the key. So that gives a user immediately an idea of how they would use this thing on the machine. Another thing about maintaining the validity of the metaphor is the way in which clipboards work in the computer. We use clipboards to do often a copy or cut and paste action. In the earliest versions of the user interface, the clipboard could actually only carry one thing. You would cut one thing from a document and it would sit on the clipboard. And if you cut another thing from the document, it would obliterate or eliminate what happens on a clipboard. When we think about the clipboard in the real world, that's not the way a clipboard works. I can just continue to jam things on my clipboard, and so I have a clipboard which has many, many items on it. So recently, Microsoft has adopted a new version of a clipboard. And if you cut and paste multiple items, you can actually have many items on a clipboard. One of the things about trying to convey metaphor is what the metaphor is good for and how you use it or how you interact with it. So we have this notion commonly of a control in the computer. So computer scientists think of controls. And one common control is something like a button, a little square rectangle on the screen. There's no reason why this square rectangle of pixels on the screen should be better than any other place. But if we put that square rectangle in a particular spot and we label it in a particular way, say like with the words OK, what we can do is convey this idea to the user that that's a spot where if they click on that thing, they'll get some action. So in this way, space on the screen is used to convey a metaphor, this metaphor of a button that you poke, push, click, or however you manipulate. One of the things about trying to create new applications and use metaphor is if you're trying to create a new application, one of the things you're looking for is a way to explain to the user how it might be used. But there's also a concomitant problem, and that is understanding how the user might want to use an application. So we talk about user-centered design as being the exploration of the user's space, how the user uses tools, like how they use a clipboard, to understand what are the important metaphors that we need to capture and then design in the computer and try and maintain the same type of consistency, the same sort of fidelity to the metaphor so that somehow we're actually implementing what the user expects. There's probably three things that you want to remember. One is that it's really important to think about what the users want to do and how we're trying to support their activity, the action that they want to do. Second thing is that metaphors are there to help convey to users what they're going to do, and that what you want to try and do is maintain consistency of the metaphor from some real world to the computer interface. And the last thing that I'd probably want to try and convey is that actually it's really hard to do that. That's one of the serious challenges in human-computer interaction, is figuring out how to represent and convey metaphors in a useful way so that users can actually use computers to better benefit.
So to understand the way the internet works, we first need to cover some general communication terms. We have two kinds of communication, synchronous and asynchronous. Now, synchronous is when both the sender and the receiver are active at the same time, such as a telephone call. You can talk over the person that you're talking to because it's happening together. Whereas asynchronous communication is when the sending and the receiving occur at different times. So think of like an email going back and forth. Now, another property of communication concerns the number of receivers. You have three different kinds that we're looking at here, with broadcast communication, which is a single sender with many receivers, like a TV commercial; multicast, which is also many receivers, but it's usually targeted to a specific group. So think of someone like signing up for an IT webinar. Now, point-to-point communication is when one specific sender and one specific receiver are on the line. So that would also be like a telephone call. So in terms of the internet, it supports what we have called point-to-point asynchronous communication. Now, this means that all of the general communication on the internet is a link between the computers connected to it. So the computers in the network become a single medium. Now, the internet's fast enough to mimic synchronous communication, but it's not truly synchronous because it does take time to transfer that information over the network. Multicasting is also possible, which will allow groups of people to communicate in something like a chat room. You can post video that can be accessed by anyone as a form of broadcasting, which would compare to radio or television, and the internet is a universal communication medium. But it also becomes more effective with each additional computer added, because every computer added is going to add another network node that can be reached. So let's talk a little bit about how this works on the back end. Now, this is what we call the client-server structure, and most interactions over the internet use this kind of protocol. So when you click a web link, your computer will get the page for you, beginning the client-server interaction. The computer is the client, and the computer with the web page is the server, which we most often refer to as web servers when surfing on the internet. The client will get its services from this web server, and then the page in return is the operation that's completed and shows up on your screen. So it sends a URL request for a web page, and then the web server will return the web page file to the computer. The internet is, like we said, primarily a point-to-point asynchronous communication system, but software has been built in to implement many forms of different communication over the internet. For instance, you're seeing the use of now telephones going over your internet connection instead of a telephone line. Now, how this works is that the software will slice up those signals coming from the computer's microphone and video camera into what we call packet-sized blocks. The content is going to be transferred to the other party, whose client will reassemble those blocks, and the sound and image will come together in a display. Now, this process will rely on very fast and reliable transmission, because otherwise it won't look like a direct connection. You will get some choppiness or pixelation, something like that. Now, as stated before, we talked about how the internet is primarily a point-to-point asynchronous communication system. But software has been built to implement the many different forms of communication that are possible. Think, for instance, a lot of people are now using telephones through their internet connection rather than a telephone line. This is an example of that, where client software will take it and slice up the signals coming from the computer's microphone into what we call packet-sized blocks. Then the content will be transferred to the other party, whose client will reassemble those blocks, either sound or image, for the display. Now, this process relies on a very fast and reliable transmission mode to make it possible. So you have to have a high-speed internet connection. Otherwise, it won't seem like a direct connection. The video or the audio could be delayed or echoed or have some other kind of quality problem. The internet protocol is generally fast and reliable enough to work, however, in most of the developed countries. So when we're talking about how this works and how one computer talks to another, we have what we call computer IP addresses. Now, each computer connected to the internet is giving a very unique address, and this is what we call the IP. There are a series of 4 numbers, one by each, and they're separated by dots. Now, here we have an example of them down in the lower range of the screen, and they're always going to go between 0 and 255. That's going to allow for billions of different unique IP addresses. But however, new IPs are, believe it or not, in short supply. Another part of this process is what we call domain names. Now, it's really difficult for us to remember the numeric IP address of all the computers we communicate with. That would be way too complicated. So the internet will use a human-readable symbolic name for computers that are based on a hierarchy of domains. Now, the domain is a related group of network computers. Let's take, for example, spiff.cs.utah.edu. So in this example, the name of my computer is Spiff. Then that's going to be part of the computer science department, which is your domain, and that's going to be CS. The next piece of this address is the University of Utah domain, which is Utah in this example above. And then the last part is an educational domain, signified by edu. So let's show how this hierarchy exists. We have 2 different examples here. Each is a member of the next larger domain, and what you can see here is, for example, edu, which is the education domain, is a peer of other top-level domains such as .com, which stands for commercial. Now we also have .org for org, for organizations, .net, .gov for government, .mil for military. So what we're doing is we're taking these names and putting them symbolic and meaningful in nature so that it makes it easier to read them than just a bunch of numbers with dots in between. Now the cloud over here on the left is really depicting the same thing. It's just showing how all of these are a piece of the next larger domain above it. So let's talk a little bit about the back side of the server side of this. What we have there is called the domain name system, or DNS. That's going to translate the hierarchical human readable names into these 4-number IP addresses. So how does my web address for edu get translated back into that 255.55 IP? Well, every internet host knows the IP address of its nearest DNS name server. So whenever the symbolic name is used to send information to a destination, your computer will ask the DNS server to look it up and match it to the corresponding IP address. So then the computer's DNS name server will translate it into the IP address, it will send it back, and then you have another client-server relationship. But if the address is brand new and it's not stored on the DNS server, the server will ask you for an authoritative name server. That will be a server which has a complete list of all the IP addresses and corresponding domain names for any authoritative name server and computers within its domain. So the root name server's address are going to be pre-programmed into the computer's software, and they're listed at www.rootservers.org together with their mirror sites. And computers can change their client and server roles all the time. Sometimes a computer can be a server, but sometimes it can also be the client. So top-level domain, or TLD, are some of those different groups that we talked about. .edu for educational, .gov for government. These top-level domains have been expanded, and they actually have a plethora of different extensions now that you can use. The full list can be found at www.icann.org. And ICANN is what is the Internet Corporation for Assigned Names and Numbers. It's all controlled and standardized, and the original top-level domains listed will apply to any organizations in the U.S. There's also a subset of 2-letter country designators, such as .ca for Canada, .uk for the United Kingdom, so on and so forth. So what happens there is, like, let's say I want to go to Amazon.com. Well, if I want to go to the Amazon page for Canada, I have to go to Amazon.ca. The TCP/IP postcard. Now, this is a way for us to wrap our heads around what TCP/IP is about. The internet's like sending a novel to your publisher using postcards. This goes back to what we were talking about with those little packets. The novel will be broken down into small units that can fit on a postcard. These postcards are then numbered to indicate where each one belongs in the novel. As each postcard is completed, it should be mailed. Now, because each of these postcards are independent, they can get to your publisher at different times. Hence the reason that they need to be numbered so that your publisher can put them back into the order that they belong. Now, because these are called packets and they take a different route, and then traffic on the network or service interruptions, that sort of thing, could delay the transmission, it has to work under any kind of adverse condition. If the packet is lost for whatever reason, the recipient computer will resend a request to have the whole message transmitted again. Now, packets can arrive out of order because they do take these different routes. And the internet will most commonly use telephone carriers for long distance connections, like fiber optic lines or separate dedicated lines. But they don't really care about how the packet is sent or transmitted, as long as it can be sent and received. The transmissions can rely on multiple technologies as the packets move across the internet and may travel on a telephone line from my house down to a repeater, then go up to a satellite in space, come back down, and go through a fiber optic line. It can take any different route. Again, the main point here is that they need to be sent and received. So the internet is basically a collection of what we refer to as wide area networks, or that can be described as a WAN. These are networks that are not geographically close. Now, the internet is also a collection of point-to-point channels, meaning that the packets have to visit a sequence of computers or hop along before they can reach their destination, unless that destination is very close in geography. Now, a local area network, or a LAN, is when computers are geographically close, and they can be linked by a single cable or a pair of wires. The Ethernet is the main technology that we use for local area networks, and it's used for connecting all the computers in a lab or a building, for instance. Now, another computing term that you may hear is a ping. Now, this is where the computer will throw out a message, and it's basically asking the computer on the other end or server on the other end to reply. Now, as we said, the Ethernet is the main thing that sets up, or that comprises the LAN, and it's a physical setup for wires, optical fibers, and the computers. Now, when we're talking about that wire that connects the computers together, we basically call that a channel. Engineers will tap into the channel to connect a computer, and this allows the computer to send a signal or electronic pulse or light flash, depending on what kind of wire it is or optical, into the channel. Now, all computers, including the sender, can detect that signal. So how do they connect to the internet? There's two basic methods. The first one is via an internet service provider or an ISP. This is how most of your home computers connect to the internet. Now, there are companies that sell these connections, things like Comcast, and way back when it used to be AOL. Now, the company places a modem or some kind of a connection device at your house, which will allow your computer to talk to its network. The modems are going to convert the bits into a computer output, which is compatible with the carrier. Now, the connection that's provided by like a campus or enterprise or within a building is where the organization will connect to the internet through usually a thing that we call a gateway. Most of us actually use both kinds of these connections. There's also wireless networks, and this is a variation of your LAN connection, but it doesn't use those cables or fiber optic wires that we were talking about before. This is referred to by a protocol name. You may hear it be referred to as 802.11, and then they have a letter designation afterwards showing the speed and capability, like ADG. The router is physically connected to the modem, and then that is connected to the internet. It's capable of broadcasting and receiving signals, and we usually do that through radio frequencies. Okay, so like we talked about before in the client-server relationship, Some computers connected to the internet are web servers. These are computers that are specifically programmed to send files to the browser that's running on another computer that's connected to the internet. Now, this huge network of web servers and their files basically comprise the World Wide Web, or why you see www in the designation of the name beforehand. These files are the web pages, and the web servers can store and send other kinds of files too, besides just web pages. The files are often used to either create the web page or help with other kind of web services like playing audio or video. So web requests work by using a client-server interaction. You will request a web page, and that means that your browser is the client asking for a file from the web server. The file can be found in looking at the URL, or Universal Resource Locator. Now, the web browsers and web servers both speak a language that we refer to as HTTP. So let's break the URL down a little bit. It has three main parts: what we call the protocol, the server's computer name, and then the page's path name. So when looking at this example above, the protocol is going to be that HTTP. That's basically telling the computer what language we're speaking. It'll tell the computer how to handle the file. Then we have the server's computer name, or the name given by the domain hierarchy. Then lastly, we have the page's path name, and that will tell the web server exactly which file or what web page we're requesting and where to find it. So servers don't store those web pages in the form seen on our screens. These pages are stored as a description of how they should appear on the screen, or basically those step-by-step instructions that we talked about in the beginning of this course. The browser will receive the description and source file, and then we'll create the web page or image that's described in that file. Now, there's two advantages to this. First of all, a description file requires less information, and also the browser can then adapt that image to your computer more easily depending on what kind of computer you are using. So what we have here is a signification of what that web page in the HTML looks like. On the left, we have that computer language, the HTML, of what the computer should, or what the web page should look like and how the computer should interpret it. On the right-hand side, you see how that page is going to be displayed on somebody's screen. Notice it has an additional image file, which is going to be required to display the web page, but everything else in this text is showing the computer how it should interpret the web page and then display it on your screen. So some web servers, as I spoke about before, have that www as part of their domain name, but some don't. And some, if you type in an address, will add that even if you leave it out. But most web servers nowadays will work either way, so you don't have to worry about typing that www.n as a predecessor to whatever page you're going to. But those web addresses, again, are just simply names that are symbolic or meaningful and make it easier for us to understand and use. All computers that are connected to the internet have a unique IP address. This DNS server will give the URL because the DNS will respond to that name and that name only. And if it can't find a match, it won't know what IP address to match it to. So that incorrect name, if you either type the name in incorrectly or the DNS can't find it, it will give you that 404 not found error. So computers can be programmed to notice this and redirect you automatically to the correct page, but that takes some programming in the back end. It won't do that automatically. So web administrators have to make sure that they register all forms of a URL. So they need to make it with and without the www. They need to have the HTTP in there. They can do common misspellings to redirect you to their current page, or something that may be more popular that people are typing in but isn't the actual web address of the company. So the way that this is organized in what we call folders and hierarchies. Now, the folder is just a named collection of files or other folders or both. This is also sometimes called a directory. So the directory hierarchy is the file structure of the computer and the forms that are in that. So think of it as a tree where the folders are the branch points and the files are the leaves. So this is what it looks like. The hierarchies have branch points and leaves, and they're often drawn sideways or upside down. But two terms are standard in computing. First of all, down means to go into subfolders, or you're going out towards the leaves, and up means to go higher in the hierarchy or towards the root. So part of the directory hierarchy is shown in the path names of these URLs. So what you can see here is an example where the page is specified by a path name that will tell the computer how to navigate through this directory to get to the file that we want to show. Each time that there's that /, we're going to be moving into a subfolder or go down a file. So we're going down in the hierarchy here to find the specific web page file that we're looking for. Now, normally the last item in the sequence of the URL is your file name, but that's not always necessarily the option or true. When a URL ends in a /, the browser will automatically look in that file for a folder called index.htm or index.html. But this only exists if the person who was designing the website named it appropriately. If it's something as small as a capital I in the name index, it won't find it. So why do we have these hierarchies? Well, most people build it to organize their own thinking and work. It's a system that we're very familiar and comfortable with, and to make these directories on the web server costs us nothing. So there's really no reason not to use them, since it makes it easier on the person programming it, and then also easier on the user to find the files that we need. So it's highly recommended, and it's considered a best practice in design. The first unit of this video, titled Connections, covers a large amount of material, including the concept of networks, the World Wide Web, HTML, digital representation, and computer basics. Exploring how the internet works, searching for information on the web, evaluating the results, and publishing a web page is a major focus in this unit. Much of this material provides a foundation for your next two areas of interaction, which are programming and databases. We'll begin our survey of information technology with a look at the technological change as compared to other human endeavors, the exploration of IT as a culture and what the digerati bring to us, how some facets of the IT culture and specifically networks have altered our society. We have a few learning objectives here, and because rapidly escalating change has become a characteristic of our society, this change is focused on where people, culture, and tools intersect. To bring about cultural change into historical context, we'll examine the enduring change from the distant past to today's increasing pace of technological change and how to approach learning in the computer culture. We'll explore common computer tools, the World Wide Web, and how networking computers together produces yet another level of change. It was not long ago when typewriters were all the rage and other quaint remembrances of just a few years ago. Whitaker states that change is a constant and inevitable, especially when it comes to technology. We observe every day in how our human actions and behaviors, both physical and mental, evolve over time. 100 years ago, no human even considered running a 4-minute mile. But in 1954, Roger Bannister was the first to smash or break the 4-minute mile barrier at only 3 minutes and 59 seconds. Then on July 7th in 1999, a Moroccan runner did the mile in 3 minutes and 43 seconds. The media everywhere reported that he smashed, eclipsed, and shattered the record. It was an astonishing improvement in 45 years. From 15 miles an hour to 16.13 miles an hour, a rate of change of 7%. To humans, this is astounding, but comprehensible. We're accustomed to seeing the best athletic performances as a way to show benchmarks for physical human endeavors. However, when it comes to computation, this idea is not as easily achieved. On average, people in their early 20s can run a mile in about 7 minutes and 30 seconds, or in other words, about twice the time that it took El Guriori. This factor of a 2 difference between average people and the world record holders is typical for physical activities like running, jumping, and swimming. No matter how hard we try, we can improve by at most a factor of 2. But this rate of change for human physical endeavors is infinitesimally small when compared to advances in technology. In the same period of time that it took, 46 years, for a one rate change of 7% improvement in the mile run, aircraft speeds have improved by approximately a factor of 200. Computer speeds, however, have completely left the charts in their factors of improvement. The first UNIVAC-1 entered the business in 1951, and this is roughly the same time period in which Bannister broke the mile record. The UNIVAC-1, the very first commercial computer, performed 100,000 additions per second. And in 1951, that was a pretty fast addition. However, in 1999, less than 50 years later, IBM introduced the ThinkPad laptop. This commercial computer, cost-effective for the average citizen, did 500 million ads per second, a factor of 5,000 improvement over the UNIVAC-1. But this computer wasn't even the benchmark for computer performance. The ThinkPad was considered a middle-of-the-road technology even by 1999 standards. Intel's custom ASCII white computer built for the U.S. Energy Department is currently considered the fastest computer and holds a world record at 12 trillion, which is a floating point, additions per second. ASCII white is a factor of 120 million times faster than the UNIVAC-1. ASCII white may not hold the record for long, however. The Scandinavia National Laboratories is partnered with Compaq in 2001 to create a computer to handle 100 trillion computations per second. So we can comprehend the factor of a 1 second improvement over a factor of a 2 improvement over a 20-year-old. But when we can comprehend the factor of 200 improvements in aircraft speeds, or even in the same time period, a factor of 120 million, it becomes unreasonable. So to put that into human terms, what we would have seen as a factor of 120 million would have meant that they had run the mile in 0.19 microseconds. Human visual perception is so slow that at that rate, they could run 18,000 miles before anyone even noticed that they moved. He would have finished the mile before the sound of the starting gun was heard, a feat that is quite literally incomprehensible. So how fast is fast enough? Do we have the capabilities to sense the difference? Most computers are underused and spend most of their time, even while being used, sitting idle. Luckily, IT tools are based on some of the common basic principles, and although the speed at which the information is processed, sent, and communicated has increased by factors of 20, 50, or even 100 million, the foundational concepts on which IT tools were created have stayed fairly stable over the past 50 years. When hardware development reaches its maximum in any given situation, software tools for processing the information will be the focus of the future development of computing power. Ubiquitous computing, or COM technology, is a paradigm shift where technology becomes virtually invisible in our lives. Instead of having a desktop or laptop machine, the technology we will use will be embedded in our own environment. That was a statement by Mike Weiser, father of the Unicomp. The rate of change and advance in technology seems to be moving at lightning speed. Factors of improvement long ago surpassed our ability to comprehend them in physical terms. So how can we keep up with the tools we depend on more and more each day? By learning how to learn about them. Fluency in IT will help us stay aware and ahead of those changes we can comprehend. So in terms of fluency, we need to have a basic vocabulary. And at its most fundamental terms, computing is concerns data, hardware, and software. Data and information are interchangeable in computing, and hardware is a physical embodiment of computation, where software instructs the computers with the steps needed to implement any kind of actions. When the Romans extended their empire from the banks of the Tiber River, the culture of much of the classical world changed forever. The effects of that change remain to this day. The legacy of the Roman Empire can be seen in modern political structures, concepts of legal administration, and even the Catholic Church. Powerful cultures have had effects on the social, political, legal, and linguistic areas of other groups that they encounter. Is information technology similar to the Roman Empire, or is it its own culture? It is certainly making changes in all arenas mentioned. Traditionally, community meant that people living in our neighborhood, or members of a local organization, or our extended family. Now, IT allows community and relationships to be defined by the electronic ties that we have with others anywhere in the world who hold similar interests, values, or job descriptions. The idea of acquaintances, family, and friends may not be the one of face-to-face contact. Each individual now has a range of options for communication with experts or development of a variety of relationship types. So in politics and law, IT culture has affected the political and legal culture of countries around the world and will continue to do so. The issue of access to government and citizen information is confronted almost daily as new methods for processing and disseminating political information are introduced. The legality of information changing hands is different from one country to another, and yet the movement of data in electronic form knows no borders. We will explore these issues in more detail later in the course. The ability to communicate with anyone in the world and for anyone to produce various IT tools seems to contradict the notion of one language, English, becoming the de facto language of IT. It is true that a majority of programs and technologies are created in English-speaking countries. However, the global nature of IT is ensuring that tools in a variety of languages are coming forward. The ability of millions of individuals to communicate with each other around the world seems to indicate that, if anything, we may expect to see variations of the most widely spoken languages develop. Consider this. Latin was the universal language in the Western world for most of the spoken and written word at one time, but the Roman Empire's use of it did not guarantee its immortality. In fact, it very likely led to its demise. Expansion of the empire and contact with so many other cultures generated variations and new linguistic paths, each with its own particular twist on the syntax and semantics of the language. Group after group adapted, changed, and altered the language to their particular customs. English, similar to its Latin in its name, was the language of IT at the beginning, but it remains to be seen if it will stay pure and dominant as the language of the IT future. The freedom of speech and assembly provided by the Internet is heralded by many and denounced by others. The virtual commons the Internet provides us every day. Consider that for every group gathering virtually to discuss the solutions to human rights violations, there is one more gathering to try to deny the very same human rights. For every individual spreading hope about life in a richly diverse world, another weaves a doctrine of separation or hate. This commons, where all ideas, regardless of their perspective, can be published, means people are no longer bound by geography or the local political atmosphere as they interact with each other. All points of view have equal reach. So what does this mean? The responsibilities of consumers of information increases exponentially because they are the ones who can determine if the information they find in the commons is good or bad for their lives. So if IT is a culture, then like any environment we might encounter as we travel or move through everyday life, parts of culture will be rich with expected behaviors, as well as tools for performing expected or desired actions. Any individual who wishes to enter and embrace a culture, taking part of its traditions, must first adapt to its customs, or in essence, they must acclimate. Every cultural environment contains norms of behavior, as well as a set of tools used to go about everyday tasks or perform actions related to some custom or tradition. Human beings are adaptable creatures and tend to evolve with and conform to the environment presented. Think about how a citizen of a country uses certain colors in their clothing to show emotion or status, or how a driver in America quickly adapts to driving his or her car on the left, not the right side of the road when visiting England. Typical cultural behaviors often involve the interaction between people and certain tools. For example, at family gatherings, there may be a custom to use a particular knife to cut the holiday turkey. Farmers bringing in a corn crop use a corn husker for the harvest. So what we need to know is the terms of endearment. Not only should you learn the right computing terms, but you should also understand how to use them to benefit from the technology. There's going to be two practical reasons for this, which we will now discuss. Humans are natural tool users. From the first use of animal bones as weapons thousands of years ago to the present day, we have been innate tool users. In fact, not only do people of all cultures use tools consistently, we invent tools all the time. For example, think about how you often use a book to provide a flat surface for writing or balancing other items when you're seated and there's no table around. Some tools seem perfectly designed for their purpose. Pick up a coffee cup. Note its shape and handle. It's perfect for holding liquids we drink or even for scooping up different materials from other containers. But complicated tools may require more training to use. Their purposes are not so obvious. We must be taught how to ride a bicycle, to drive a car, or to ski. Of course, some people don't seem to even need that. The more intricate the tool may require more training than a single person can give. So instructions are written specific to their use in certain situations. For example, most appliances and other intricate tools come with an owner's manual. With whole tools, one thing is clear. Certain behaviors and actions using those tools will be correct or achieve the desired result, and others will not. Learning what actions and behaviors should accompany various tools is a key element of acculturation. So we tend to learn through behaviors and or mental processing in three general areas. By watching others, we learn from their actions and the reason why they do as they do. By analogy with other environments, we develop intuitions about how things should be done based on similar actions elsewhere. And by trying things and learning from what happens, even our mistakes. We accumulate experience known as tactic knowledge from actually trying out certain behaviors or customs and becoming familiar with them. So by giving names to computer features that we know intuitively, we can explain how metaphor is used in computing and how it helps us understand computing algorithms. So how do we learn to use complicated tools? Well, in almost exactly the same way we learn about anything else. It doesn't really matter what the tool is or what format it is presented to us. We adapt and learn tools by accumulating experience, developing intuition, and reasoning. Thus, we can figure out how to use some tools without reading the owner's manual. For example, if you're given a portable MP3 player, you can easily figure out if you've previously used something like it, or a portable CD player, stereo system, or something in your car. That is, if you can remember back when those were used. The product designers and software designers both try to make technology so simple that members of a technological society can guess its operation using only their experience, intuition, prior knowledge, and reasoning. A well-designed tool can be intuitively used. Designers play off the intuition and experience of their audience, and information fluency depends on getting to know the tools used in the IT culture, learning where and why you use them, and just as you learn to use a vacuum cleaner as a standard tool to aid in the task of cleaning a carpet, you need to learn to use the tools that will aid you in your lifetime task of processing information. One of the tools we use to assist us in this is algorithms. We use algorithms all the time to solve our problems. It's a precise systematic method for producing a specified result. The thing is that programmers make algorithms precise by writing them in a programming language, but people often make algorithms. So to turn this computing stuff into things that humans can understand, we use metaphors. Most interactive software today uses a graphic user interface, GUI, which is pronounced GUI. A GUI does as its name implies. It allows a user to interact with it through the use of graphics and images combined with some text. So consider this GUI interface as shown. Can you guess what the software does and how to use it? What are other analogies used in software today to help users adjust and learn quickly? What is it that makes learning any tool, like the software example here, an intuitive process? For us to figure out a piece of software, its behaviors or actions must be consistent with their previous experience in the task we wish to do. Software designers know that the success of a product depends on how intuitive it is to use, and what good test is whether the software's basic behavior can be determined without consulting a manual. With well-designed software, users should be able to figure out a good deal about how the software works on their own. Software with a good interface design is immortal, so to speak. The design of the tool will be mirrored and become part of the fabric of all similar software tools for as long as it matches something innate to human experience. The visual analogy is obvious if you're already familiar with a physical CD player, as illustrated in the book in Figure 1.2. The metallic-looking buttons enhance the idea that they're identical in form and function to those of a real CD player. The CD slot, displayed further, supports the analogy that this piece of software will play music, but most users figure out quickly how to find the actual opening for a CD on the computer tower. The slider bar indicates a way to increase or decrease the volume, and as the slider moves up and down, the volume of sound provides immediate feedback. The icons or images on the control buttons are familiar. They are standard features on electronic tools that play music. For example, the single pass icon changes to a continuous loop icon, and when clicked, suggesting its meaning. The names on the mode buttons are suggestive of the capabilities of an audio CD and can be guessed, and the single pass icon changes to a continuous loop icon when clicked, suggesting its meaning. So most desktops of today are just another version of a GUI, and current GUIs are being built using some standard behaviors. Anyone who's used MS Word will see that many of the behaviors are also seen in the CD player interface. The act of pressing a button in the real world and pushing one on a computer screen brings up another point. You need to only press a button once to call the elevator or to request a green light to cross the street, and usually the same goes for virtual buttons or in software interfaces. Pressing more than once will usually lead to confusion for the program. The Mac first introduced the mouse to the public, another component in the desktop metaphor, but Apple did not invent it. Actually, Stanford Research Institute invented the mouse in 1968. And when it was introduced, it was stated that they called it a mouse and didn't know why they didn't change the name. Now, menus present the functionality of an application. They usually divide the behaviors of the tool into general categories. There are pull-down menus and pop-up menus, and for each there are standard behaviors that should always apply for certain activities. Notice the ... or ellipse, and the keyboard shortcut Control-X. The ellipse indicates that there are further operations to select from for that menu choice, whereas the shortcut codes allow you to perform the specified action without using the mouse. You can just use the keyboard. So how can you distinguish between a case when the computer or program is busy working on your task and the case when it's patiently idling, waiting for you to give it another command? It's based upon feedback. Feedback is given in a number of forms. For example, when you're saving a particularly large Word document, the bottom of the Word application screen will display like a bar shown here. The blue rectangles will slowly advance to the right as the application writes your information into the storage unit you have chosen, whether that be a hard drive, a USB, or server. Well-designed computer tools will always give you feedback indicating their state of activity, the task they are performing, and alternatives. If the tools are especially well made, you will not have to look very long to see if the computer understood the command you gave it. In general, you should watch for color or shadow change, an icon change, title change, or motion as indications that the computer is working for you. For example, think of the rotating world image that displays in the upper right-hand corner of the Internet Explorer web browser when it's retrieving a web page that you requested. So as we talked about before, exploring and trying things is the best way that we can learn how to use a new tool. So exploring the environment is one of the easiest ways to learn a new piece of software. Like any new culture or new tool, it will take a moment to explore the new environment. So with the expectation that much of the culture can be observed and tested, you do your own exploration of the environment. When you have a computer program, such as Windows Media Player or QuickTime, you can open it up and see if your computer can figure it out with going on to the online manual. Ironically, most beginners think that they should check the manual, even though it's often most useful just to experiment. So, if there's one fundamental rule, it's this: you can't break the computer unless you drop kick it out the window, or perform some other act of physical violence. The way to learn the operation of the application is to try it out, so explore. Check out each of the menus and see what behaviors can take place. See if you can guess what particular buttons will do when pressed. When you press them, were you right? Even though nothing will break, it would When starting to use a new piece of software, like any new tool, we usually take a moment to explore the environment. The consistency provided by software engineers gives us a strong sense of familiarity when using new applications. Usually two important activities are performed. Clicking around is exploring the application to see what kind of features are available, whereas blazing away is trying the application in a way that we haven't done so before, clicking on each of the menus and seeing what kind of behaviors can take place. When creating a new instance, we can usually use the File menu to find a command called the new. This will create a blank instance of the kind of file that the application creates. Now, while exploration is the best way to learn a tool, there are some tips that will make our learning experience go much smoother. First of all, we want to save early, save often, and create a backup. We need to make sure that once we've created something that we like, we're creating copies of the work at steady intervals so that we don't lose our work along the way. We need to have common expectations that it's not going to be right the first time. When we're frustrated with the tool, get away from it for a while. Now, if you ever run into any issues, a hard reboot, which is shutting the computer all the way off and then turning it back on, will solve most problems when the program acts up. Then practice safe computing. There's a lot of buggy software out there that's available for free on the internet, and a great many viruses are sent in emails, so we need to be careful about what we download, open, and save. We're going to be talking a little bit more on viruses and bugs later in the lesson. So no matter how fast a computer is, if it doesn't have the right software, it may as well be a doorstop. Anything is only useful if it has something to... No matter how fast a computer is, if it doesn't have the appropriate software, it might as well be a doorstop. A VCR, DVD player, and TV are only useful with tapes or discs or movies or television shows to play on them, whereas a stereo system is only useful with CDs, records, tapes to play on them. So no matter how fast your computer is, if it doesn't have the right software, it may as well be a doorstop. Nothing is going to work without the functionality that is No matter how fast your computer is, if it doesn't have the appropriate software, it may as well be a doorstop. A DVD player, Blu-ray, or gaming system is only as useful as the games, movies, television shows, or discs that play on them, whereas a stereo system is only as useful as In the same way, software, the collective term for computer programs or applications, makes computers useful to us. By running different programs, we can use computers for a surprisingly wide variety of purposes, from writing papers to modifying images. To use a computer effectively, we need to know what kinds of software are available and what the purposes of each software application is. Some common pieces of software that you're probably familiar with are things like spreadsheets, which do calculations and analysis on tables of numerical data. These are programs like Microsoft Excel, Lotus 123, Corel's Quattro Pro, and OpenOffice. Another thing that most people are familiar with is the word processor. This is used to edit and format documents, and familiar common software platforms are Microsoft Word, Corel WordPerfect, or OpenOffice. Database software is for storing and extracting structured information, such as an online library catalog. Familiar terms here are Microsoft Access, Oracle, IBM DB2, and MySQL. We also have image editing, which is for creating and modifying images, including computer-generated images as well as photographs. And things like that is like Adobe Photoshop or Corel Draw. The software stack is a concept used to structure and organize the software in a contemporary computer system. They are a series of layers of programs that implement user applications. Each layer implements the operations used to build the layers above, and they increase in complexity from bottom to top. You can see that to check out a video on YouTube using a smartphone, it goes through the different layers of the software stack. Now, random access memory, or RAM, stores data using electrical current. What that means is when the power goes off, the information will be gone. Whereas disk drives store the data magnetically on round platters, hence the name disk. So when the power goes off, your data is still there. Now, unlike random access memory, disk storage does not get erased when the computer is powered down. Disks are less expensive than RAM per gigabyte of storage unit. However, disk drives are much slower. So to make a program run as fast as possible, its instructions are copied into the RAM. The processor will read and execute these instructions from RAM, and all of this happens very quickly, so you can't really see the RAM being used. We want as much RAM as possible to hold as many program instructions as possible, but RAM is limited. So someone came up with a scheme to make it possible to increase the amount of RAM using space on the hard disk. You may have heard the term virtual memory before and wondered how it differs from RAM. Well, virtual memory is called virtual because it's not the same kind of memory as RAM, although it is used for the same purpose. Especially now, when most computers run several memory-intensive programs at once, it is common to run out of RAM. RAM is much more expensive than disk space, so some clever computer designers invented a scheme where a certain amount of hard disk space can be used as extra RAM at the expense of speed, of course. This special disk space on the hard drive masquerades as extra RAM, and it's called virtual memory. Some people call RAM physical memory to distinguish it from virtual memory, but the RAM that is sold with computers is actually a combination of RAM and virtual memory. So just like almost everything else in computing, the storage capacity of the hard disks increases every year. Some way of organizing our disk storage is necessary for us to take advantage of such. So just like almost everything else in computing, the storage capacity of hard disks increases every year. Some way of organizing our disk storage is necessary for us to take advantage of such large amounts of storage space. In real life, in a brick-and-mortar office, a file usually means a folder for holding papers. When discussing computer files, a file is defined a little differently. It's one basic unit for storing and organizing data on a disk. And more precisely, a file is the data on a disk storing a single document. Computer files are different than files and folders in a filing cabinet because each file is only one document. Each folder holds several files. And even if you name your files carefully so you can quickly identify their contents, a collection of more than several dozen files will probably be difficult to maintain. In real-life offices, documents are not kept in one enormous pile, but they're divided by subject and stored in folders or filing cabinets. This type of organization is called a hierarchy, with multiple levels and categories and subcategories. What we have here is an example of a folder hierarchy. You can organize the files on a disk hierarchically by using file folders, also called directories, or just folders. The file folder is fundamentally different than a file, and the directory is a container for multiple files and other directories rather than the data for a single file. They are called folders because folders in real life serve a similar purpose. A folder itself is not a document you can read, but it holds documents and perhaps other folders inside it. By grouping related files together and creating directories to store them in, you can make them easy to access for future use. So think of a path as a sequence of folders you need to open to get to the file you want, starting from the drive. You might consider doing the same with your own documents, either paper or electronic, as shown in the example of the hierarchical file organization. But this type of organization is very common in computing. It's used in disk storage and also in the Start menu, and you'll see it again. And you'll see it again when we're working in networks and programming sections. So when you organize the folder, normally the last item in the sequence is the file name, but this isn't necessarily true. When the URL ends in a /, the browser will automatically look in that folder for a file called index.htm or index.html. But that file will only exist if the web designer built it. In addition to understanding the hierarchy of file structure, we also want to talk a little bit about file types. Although all programs save their data on disks as files, they often store them in a special format, which is a way of encoding the information. File format is also known as file type, and it's shown under this name in the Windows File Property dialog. The simplest file format is what we call plain text. And this is the format that Notepad and other text editors use, which you will be using to craft your HTML. Now, files of this type are conveniently named with the .txt for text file name extension. And in Windows, every file format has a corresponding file name extension. Each file is displayed with the icon or a small image associated with the program used for the file format, such as the little spiral-bound notebook for Notepad. So programs are read from the disk into RAM when they are run, and programs, just like all other data on the disk, is stored as files too in their own format with the .exe extension. .exe is short for executable, since execution can be used to refer to the process of running a program. Notepad cannot open word processor document files such as those in Microsoft Word format because they're in a format different from plain text that includes data for text styles such as bold and underlining in addition to the text itself. So, although Microsoft Word can open Notepad files since it's a basic plain text file. A network is two or more computers connected together. Networked, they're much more useful than a single terminal, which only has access to the data stored locally on its hard disk, or something that's inserted into the DVD or through a USB drive. Many different types of computers can be added to the network, and the specifics on how computers work will be covered later, but for now, think of them as having many different forms and many names, including many similar components. Networks give each computer connected to them the ability to access more information and software, help users communicate and exchange information, perform services for one another, including sharing printers or giving access to email. And networks can also change our ideas about social interaction. Computer networks are an implementation of our natural tendencies to communicate outside our immediate location. With our networks, we can communicate with our family, our friends, our coworkers, but we can also communicate with people all across the world. Physical communication outside of our network mimics that same interaction between the computers and the users, often on a much larger scale than we could ever hope to achieve in person. So the reality is that most networks we deal with every day consist of tens, hundreds, or even thousands of computers connected together. And those computers come in all shapes, sizes, and types. We have laptops that are used for portability, desktops, which are usually used in offices or labs, and servers that can provide us access to email, web pages, applications, and file storage. All of these various computers allow us to send email, transfer files, and access the World Wide Web. Now, in networks, we can exchange more than 500 billion bytes of data per day per organization. Half of this exchange data goes or comes from the mother of all networks, known as the Internet. There are a variety of ways that computers can be physically networked together. So let's start by looking at how computers in a local area network, or LAN, are connected. Computers that are all connected physically by a wire, wire pairs, or some other physical connection are known as local area networks. LANs are not necessarily connected to the Internet. They are simply a common way for organizations to share resources. Computers are connected for very specific reasons in these settings, either to share resources, such as printers, or to pass information from terminal to terminal. The most dominant connectivity technology for these smaller networks is the Ethernet. This is not the most efficient form of networking available, but because of the capacity of the Ethernet wire to transmit large chunks of data, we usually don't notice much difference between heavy and light network traffic on these internets. Ethernet sends extremely large amounts of data and information across the LAN, one computer at a time. If two or more computers attempt to send at the same time, they're alerted to the presence of the others and they stop. They do this always detecting. The most dominant connectivity technology for these smaller networks is the Ethernet. This is not the most efficient form of networking available, but because of the capacity of the Ethernet wire to transmit large chunks of data, we usually don't notice much difference between the heavy and light network traffic. Ethernet sends extremely large amounts of data and information across the LAN, one computer at a time. If two or more computers attempt to send at the same time, they're alerted to the presence of the others, and they stop. They do this by always detecting the information on the line at the same time that they are sending. And if the information received differs at all from the information sent, the computer will stop sending, wait a moment, and then try again. This technology is actually extremely inefficient and would not work well on a large LAN or a wide area network, which is called WAN. So most home users connect to the internet by ISP, or Internet Service Provider. These are companies that sell connections to the internet. The company that places a modem at your house, and then the modem converts bits into computer outputs that form. Most home users connect to the internet by ISPs, or Internet Service Providers. These are companies that sell connections to the internet. The company that places a modem at your house will sell the internet to you, and then the modem will convert the bits a computer outputs into a form that's compatible with the carrier. Now, how networks connect to the internet is with subnetworks or subnets. This might be a single LAN or several LANs brought together under one logical name. So like most organizations, our organization usually interconnects the computers in the UW domain at .washington.edu, which is connected to the internet via a gateway. A gateway does just as the name applies. It acts as a gate to another sphere or space, and in this case, the world of computers that make up the internet. A gateway is a computer or series of computers that handles all initial internet traffic headed into or out of any computer sitting within the washington.edu domain or any other series of related computers. The gateway usually receives data from the outside the domain from a series of switches, which are also called routers, and these are the specific types of computers on the internet designated to direct the traffic. So in our book, we saw how every computer on the internet has a unique numeric address called an IP. The IP address is actually composed of 4 numbers, and each ranging from 0 to 255, separated by periods, which we read as a dot. You have probably already heard the terms web server and email client, but you might not realize server and client are general terms that describe the roles computers can play on a network, depending on what software they're running. In general, a server is a computer that provides some kind of data, such as web pages or database entries, or a service, such as email or printing, whereas a client is a computer that requests and receives the data or the service. To illustrate this difference, we will begin by discussing an example with web pages. When you view a web page on your computer is acting as a client to a web server somewhere on the internet, the computer where the web pages are stored. Each time you click on a link, your web browser sends a web page request through the network to the web server, and then the server responds by sending a copy of the requested page back to your computer, where the browser will display it for you. So most interactions over the internet use this client-server interaction protocol. Now, as far as protocol, that is prescribing a strict adherence to correct etiquette and precedents, as in diplomatic exchange in the military services, or it's a set of conventions governing the treatment and especially the formatting of data in an electronic communication system. Now, the internet, like most information technologies and applications, follows a variety of protocols. Both definitions of protocol will apply to the world of IT. The Internet cannot exist in its current form without protocols determining how information is sent, processed, and communicated. The Internet isn't the only area to use protocols. All information technology applications, such as software programs, also use protocols for determining how information will be sent, processed, and communicated. Now, web browsers use a protocol called HTTP, whereas email will use SMTP, IMAP, or POP protocol, whereas things like Gopher will use FTP protocol. We'll get into some of these protocols later as we explore HTTP. The term web server can be confusing because it's often used in two different ways. The term commonly refers to a computer running software that enables it to send or serve web pages on request, such as in My Home Pages on the web server students.washington.edu. Some people also use the term web server to refer to the software rather than the computer itself, as in, you're running a Microsoft web server on your computer. You should regularly check for security problems. So the context will usually distinguish which way they're using it. So with all the millions of hosts in the EDU domain, subcategorization is necessary. The rightmost part is sometimes called the second-level domain and specifies which educational institution within the EDU domain this host belongs to. In this case, it's Washington, and that corresponds to the University of Washington. Every college and university with computers on the Internet has a special name that identifies its group of hosts within the EDU domain. That is UMICH for the University of Michigan and UCLA for the University of California in Los Angeles. A typical education institution has so many hosts that yet another level of subcategorization is used, usually basically on academic departments. The next part of the host name, CS, indicates that the host is in the computer science department. Other departments at UW and their corresponding third-level domain names are things like music, physics, astronomy, and School of Nursing. Finally, the www part of the host name specifies the particular computer within the domain cs.washington.edu. In this case, the www is the name of the computer that serves the web pages about the Department of Computer Science and Engineering at UW. It's typical for computers that serve web pages to be named www within their domains. We will learn more about what a web server does later, but these levels of subcategorization should make it easier to remember www.cs.washington.edu than to remember the corresponding IP address, which is 128.95.4.112. We will start with a few small experiments with host names and IP addresses to learn more about how they correspond to each other. So at the heart of each of these requests is what we call a URL, which is short for Uniform Resource Locator. It's just a standard way of specifying a file or a resource on a particular computer of the network. URLs can be used to specify many kinds of network requests, but because they're most commonly used for web pages, URLs are also called web addresses or links. URLs appear everywhere now, in advertisements, on local television broadcasts, and even on boxes of cereal, as companies and other organizations set up their websites to accompany traditional media materials. Every URL includes three important pieces of information. First, what kind of request it is, usually for a web page. Second, the host name of the server to which the request is going. And third, the location and the name of the file being requested. Now this example shows the hierarchy of these domains. Each is a member of the next larger domain. So you can see here they're both just two different visual depictions of the same thing. These names are symbolic and meaningful to make it easier to read for us than those IP numbers, and obviously much easier to remember. So what is the Internet? The Internet can most simply be described as a network of networks. In fact, it's a worldwide system of computer networks, and it's the mother of all networks. It was and has always been an infrastructure to support all kinds of communication. If you just look at the implementation aspect of the internet, technically it's all computers using the same communication protocols so that we all speak the same language. That protocol is known as TCP/IP, which is the Transmission Control Protocol Internet Protocol. TCP/IP is the basis for information exchange on the internet and is the media and application independent. It's physically the internet and the totality of wires, fibers, satellite links, switches, connecting named computers to each other. So what are you seeing is just the number of host computers currently on the network and the number of users accessing these host computers. These computers are often connected through a specialized computer that we call a web server. These are computers programmed to send files to browsers running on other computers connected to the internet. And this is what comprises the World Wide Web. So the web requests use client-server interactions. They request a web page, which means your browser is a client asking for a file from a web server, and the file can be found in looking at the URL. Now, since they both speak HTTP, they're going to be able to communicate with each other and show each other what you're requesting. The URL has three main parts. The first part we talked about is protocol, the HTTP, and that tells the computer how to handle the file. The second part of the name is the server's computer name, or the name given to it by the domain hierarchy. The last part is the page's path name, and this will tell the server which file or page is requested and where to find it. So servers don't store the web pages in the form seen on our screens. The pages are stored as a description of how they should appear on the screen. The browser receives the description or the source file and then will create the web page image that is described through the browser. There are two advantages to storing and sending this as the source rather than the image itself. The description file usually requires less information, which means it's smaller, and the browser can adapt the source image to your computer more easily, meaning that not everybody is going to be using the same browsers or the same hardware, so it has to be able to adapt to whoever is using it. Now, the domain name system, or DNS, translates the hierarchical names into those IP addresses. So every internet host knows the IP address of its nearest DNS name server. Whether the symbolic name is used or the computer asks the DNS server to look up the IP address, doesn't matter. You're going to get the same result. When your computer asks the DNS name server to translate a name to the IP address, it's just another client-server relationship. If the address is new and not stored in the DNS server, the server will ask an authoritative name server. This server keeps the complete list of all the IP addresses and corresponding domain names for all the name servers and computers within its domain. So to summarize, some web servers have www. as part of their domain and some don't. One analogy that we like to use to describe TCP/IP is that the internet is like sending a novel to your publisher using postcards. The novel is broken into small units that will fit on a postcard, and then these postcards are numbered to indicate where each one will belong in the novel. When each postcard is completed, it is mailed. So basically the rules of the road here is that the process uses the Transmission Control Protocol and Internet Protocol, or TCP/IP. The data such as email, web pages, or phone calls, or anything sent over the internet is broken up into little units called packets. This is the TCP level of the protocol. Each packet contains an IP address, a sequence number, and some of the actual information, like part of the whole email message. The other part of the protocol, IP, deals with the destination alone, and it's contained within the packet structure. So packets make their way, usually by different routes, to the destination computer where they are reassembled in order to reconstruct the original message. So in our analogy, sooner or later the publisher receives all the postcards, but not necessarily in sequential order. They didn't take the same route, and the cards are finally arranged in order, and then your publisher can see the entire novel in the order that it was meant to be. The TCP/IP protocol doesn't care what media carries the packet. In this way, it's media and platform independent. For example, the packets that make up a single email message sent from a computer in Washington to one in Florida might travel across phone, cable, or fiber optic lines. It may go up to a satellite transmission or over a cell tower, but the message will still get to its destination. So one of the key components here are that packets are independent. Each packet can take a different route, and congestion and service interruptions don't delay the transmission because of this independence. So when the packets are sent from computer to computer, how does the sending computer know where the receiving computer is? Well, that's what the computer needs it to communicate with, is the IP. The internet implements that point-to-point communication, and it requires a unique destination address, meaning the receiving computer needs that unique name. So people like to use words when assigning a name to something because that's what we understand best. Computers only understand numbers. Later we're going to talk about exactly how they understand them, but first let's figure out a solution to this problem. Named computers, or those on a network, actually have two names: a logical name, which is for us to understand, and a physical name made of numbers for computers to understand, the name for computers by computers. Now, if there are only a few destination computers, people could probably memorize the numbers assigned to those few computers. But since there are so many, literally hundreds of millions of computers on the internet, we can't remember all those numbers. So when we're moving these packets, the internet will use telephones for long-distance connections, fiber optics, and separate dedicated lines for high-speed connections. The computers that don't know or care about how the packet is sent, as long as it can be sent and received. And the transmissions may rely on multiple technologies as the packets move across the internet. Now, top-level domains is something that we talked about a little bit earlier when we were talking about EDU. Now, the top level is just things like biz, info, name, travel, and others. The full list can be found at ICANN, and this is the Internet Corporation for Assigned Names and Numbers. The original top-level domains listed apply to all the organizations in the U.S., so you'll see that there's also a set of two-letter country designators for other countries. For instance, if you're loading Amazon in the UK, it's going to be amazon.uk instead of amazon.com. Next, up to this point, Up to this point, this video has been dedicated to the discussion of the internet. You've seen how computers network with other computers, and how networks of computers network with other networks to form the internet. Often people make no distinction between the internet and the World Wide Web. However, there is a difference. The World Wide Web is only a small portion of the internet, and it's the part of it we see when we surf the web. In part 3, we're going to be exploring the protocols and underpinnings of the web. We'll look at browsers, hosts, URLs, and web publishing. And the final part of this lesson will be a hands-on look at web publishing. You will build your own web page, upload it to the new web host, and publish it to the web. Here are two general descriptions of the World Wide Web. The first is a philosophical interpretation of a fairly new phenomenon, and that is that the World Wide Web is the universe of network-accessible information, an embodiment of human knowledge. The second is the identification that one detail separates the www from the internet, which is all the resources and users on the internet that are using the Hypertext Transfer Protocol, or HTTP. In addition to the above, the World Wide Web includes all computers, called web servers, capable of sending information to your browser. And in most domains, this web server is called the World Wide Web. However, a web server can have any name. Student pages at the University of Washington are stored on a server with the logical name students.washington.edu. What is most important about web servers is the fact that each and every one uses the same protocol to connect to another web server and exchange web page information, HTTP. It's not the only protocol that web servers use, but it is the only one that distinguishes them from other types of server computers on the internet. And in a more general sense, we can say that the World Wide Web is all web servers and their files that communicate using HTTP. You've heard the word server used over and over in this video, and in web servers, email servers, and file servers. Where does it come from? Well, the idea of a server and the clients it serves is actually a lot older than internet and the World Wide Web, but it's become incredibly popular in the last 10 years. This model has become the standard for most networks, and it includes the internet. It allows for certain centralized computers and servers to hold and provide software and services for many requesting computers or clients. So again, to review, a client is any computer that requests information. This could be a request from a web page, for email, for print services, or a particular printer, for instance, or file storage and access. A server is any computer that provides a service. This could be sending out a web page, allowing access to download, sending a file to print, or storing a file. A simple explanation of the role of a server is that email servers provide email services to various client computers, whereas web servers provide web services, print servers provide print services, and so on. A web browser is an application that uses the HTTP protocol. This application allows people on client computers to interact and look at the requested information on the World Wide Web. Netscape, Internet Explorer, AOL, and Opera are all examples of web browser applications. Each of these applications offers what we call a graphical user interface, or GUI, such as the one shown here. Web pages are just glorified text files containing the instructions for your web browser on how to lay out, format, and display the web page. These instructions are written in a special language that we call the Hypertext Markup Language, or HTML. Hypertext is text viewed on a computer that includes connections called hyperlinks, or more commonly, just links, which can be selected to jump to other documents, images, and other files. Hypertext existed long before the web in the form of documents linked to other documents on the same computer. Without using the network, it became much more popular with the advent of the internet and web browsers. So the basic HTML syntax is a key concept of the web browser, and it's the job of the web browser to read this HTML source and display the page it describes. HTML has some characteristics of a programming language, but technically it's not one, strictly speaking. The main difference is that HTML is used to specify the structure of a web page, such as its title, paragraphs, and images, and how it should appear in the web browser, whereas a programming language is used to specify what the computer should do in the form of instructions. Like a programming language, HTML has special words and punctuation that must be very carefully used for the computer to understand them. These special words and punctuation, combined with the rules for the proper usage, known as syntax, is a word we're going to see again and again when we discuss programming. Syntax is a lot like the computer equivalent of grammar for a language like HTML. Formatting is done with what we call tags. These are just abbreviations enclosed in angle brackets. Many tags come in pairs, and the second pair comes with a /. In HXML, the tags have to be lowercase, and if it is in any other form, it's going to be an illegal syntax. It's not going to be able to be read. So the tag pair surrounds the text to be formatted, much like a parentheses would. So when we format with tags, we usually use a descriptor name, like for instance, title. The title tag will be enclosed within the angle brackets, then the title will be displayed with the close / angle brackets, and then the name of the tag again. These tags can be read as this is where the title starts, and then this is where the title ends. It's basically those instructions to the browser of how this should be displayed. There are two ways that you can view HTML. We have either the web page or the source. Think of the source code as a description of how the web page should look. Each web browser will interpret the description just a little bit differently, because web pages viewed with like Internet Explorer will sometimes look a little bit or even a lot different than web pages viewed in Chrome. The reason for these differences is based on the version of HTML that the browser is using to interpret the source code. HTML is currently now in its 5th version, but all browsers don't use all available types in their version. For example, some interpretations of what a word or term means varies according to the browser. A web page is the file consisting of the plain text that follows the syntax rules of HTML. So here's a very simple example web page as viewed in a browser window. See that the address on the page is shown as a path name and not a URL. This is because the web page sample.php is being viewed locally from the temporary folder on the C drive instead of a web server. Although web pages are conveniently viewed via the network from a remote computer called a web server, web pages are actually files that can be stored on disks, just like any other file would be. So in the HTML source code shown here, you can see that there's a lot of content, word, and phrases that seem to be marked up with an odd set of terms and characters. For example, there are some TD characters and the terms head or body in various locations. The common theme with all of these terms is that each will begin with those angled brackets and end with an angled bracket. In addition to the text to be displayed, the source contains the HTML tags placed carefully in the text. Words such as body, H1, P, and EM do not appear in the browser, but they will affect how the text they surround is displayed. The HTML tags above are indicating that at this point in the web page there should be a new paragraph. The text at the start of that paragraph will be set as bold, and then the bold markup will stop right after the text 2002. The paragraph will continue until just after the text students and then end. So some of the key concepts with these HTML tags are knowing that they are special markers that control text formatting. So things such as boldface, tables, centered. They also include non-text items such as images and links. The tags are enclosed in those angled brackets. And if you look carefully at the tags in this example, you will see two kinds of tags that exist in HTML, what we call paired tags and unpaired tags. Paired tags are used to mark sections of the text as opposed to just a specific point in the text. For example, the text between a paragraph tag, which is the P, and the next /P tag is treated as a single paragraph. Since the first tag without the slash denotes the start of the paragraph, and then the other tag with the slash denotes the end of the paragraph. In general, we call the first a start tag and the other an end tag. Other paired tags used above include EM, which is bold, and strong. These are used to indicate that certain sections of the text should be emphasized. Unpaired tags, or singleton tags, are tags that are not paired. These generally are used to denote the insertion of some non-text item in the web page. In the example here, we see that the HR tag is used to insert a horizontal rule, which is just basically a thin horizontal bar stretching the full width of the window on the page. There's no /HR tag because it doesn't make sense for a horizontal rule to contain text. It's just a line. So it's used as an unpaired or singleton. Web documents can be formatted in many ways, and each formatting feature requires its own tag. Programmers and web designers need to remember a few common tags, and uncommon tags can be looked up at w3schools.com. Now, HTML has some specific work rules, but once you learn them, it can be quite simple to use. All HTML documents will begin and end with the HTML tag. Content that a user will see should go inside of the body tag. Information about the HTML file itself should go inside of the head tag. And all closing tags add a / just before the tag term, such as /P to end a paragraph. All HTML tags must be properly nested. Another way of saying this is don't cross your streams. If you've opened up one tag, then another, do not close the first one before closing the second. In other words, close the inside tags first, then close the outer ones. So here are some examples of the different HTML formats. Think about the process you're using when editing a term paper or another written report. You probably write or print out a rough draft, then read it through to find errors or improve the format. Often you mark a point where the new paragraph should start or where a larger font should be used. Creating HTML is like this process, but it's done with the world to see, not just your English professor or employer. Don't use a word processing program like Word or OpenOffice or any other program that's meant for documents, because what that's going to do is insert some junk code into your HTML. So when you write HTML, you want to either use a web authoring program or a simple text editor like Notepad with special tools like FrontPage or Dreamweaver. Now, for learning the structure of a markup language, you're going to be using simple text editors like Notepad++ when you create your web pages for this course. Most HTML tags can be combined freely, as you saw with the LI sections containing text formatted tags and link tags, but we can try other combinations in the web page. You can list nested lists inside of a list. You can list small images, or you can list links that are images instead of text. But these are going to be the minimum requirements for a web page. No matter what, every web page is going to have HTML, head, body, and all of those tags will be closed. So text editors simply figure out what language you're writing in and then add color to your code to make it easier for you as the web designer to read. Operating systems come with standard text editors like TextEdit, which is on the Mac, or Notepad with Windows. Text Wrangler for the Mac and Notepad++ are better programs and have more features, and both can be downloaded from the internet for free. So let's move on to programming, telling the computer exactly what to do. Here we want to explain some of the similarities and differences among algorithms, programs, and heuristic solutions. The first part of this video covered a large amount of material of networks, the World Wide Web, HTML, digital representation, and computer basics, exploring how the internet works, searching for information on the web, evaluating the results, and how to publish a web page will be a major focus. This portion of the video will include logical components of technology, including how decisions are made and how computation is performed on the data. We'll continue our exploration of information technology by thinking about algorithmic thinking, which is how to write clear instructions, programming basics, which are the universal concepts in any programming language, branching and functions, which are programming the computer to follow different paths or make decisions based on various conditions, and iteration and arrays, which is programming the computer to loop through lists. Programming in its most basic for the logical component of technology includes how decisions are made and how computation is performed on data. So has there ever been a point in the creation of your web page where you wish the page could interact or respond to the interactions and questions of a user in some way? HTML pages you create are normally static. They don't change unless you go back into the source file and make a change to the HTML. So wouldn't it be nice if your page could dynamically change on the fly based on certain actions by user? HTML alone can't do that. But if we introduce the concept of programming into that HTML, we can create a web page that incorporates the features about computers that make them the most useful, including the ability to follow instructions over and over based on some kind of input. As the input changes, so might the result of those following instructions. So an algorithm is simply a precise symptomatic method for producing a specified result. These are the steps that a computer goes through to solve a problem. To be effective computer users, we need to learn the process that the computers use, and thinking algorithmically is our first step. An algorithm has two main parts: giving the instructions and following the instructions. So in this course from now on, we're going to consider giving the instructions, specifying the algorithm to be the programmer, and following the instructions or executing the algorithm without the help of intervention of the programmer is going to be the computer. We must always assume that the agent giving the instructions will not be the same as the agent following them. As programmers or teachers or parents writing instructions for the babysitter, we're not just jotting down notes for ourselves. Rather, we're explaining to someone else, or the computer in this instance, how to do something in a step-by-step fashion. This assumption that we're not writing for ourselves forces us to write the instructions with a level of precision that we may have not used before, and that's okay. That's what we're going to learn next. So not all processes given in the example in our book are algorithms. The process to find information on the web using a search engine isn't an algorithm because it's not symptomatic. It's guaranteed, and it's not guaranteed to find it. The process could fail. So what we need is a helpful procedure for finding that result. Think in detail about some of the things you do every day. As you read the following everyday algorithms, visualize trying to follow the steps listed in each and what kind of results you will achieve. Think about what assumptions are built into each algorithm. A simple algorithm that most people can relate to is a recipe. That's an example of an algorithm written by chefs and followed by cooks to produce a specified food. Some recipes are less precise than others, and examples, wow. So we're at the point in the course now that we can configure your computer for writing HTML. We want to check that two programs are installed. First of all, a browser, and second of all, a text editor. Now, browsers are things like Internet Explorer, Chrome, Firefox. You'll notice that in our textbook, he uses Firefox mostly, so I'm going to stay consistent with that. As far as text editors, he uses Notepad++ for Windows or Text Wrangler for Macs. Now, Notepad++ and Firefox are both free, and they're preferred for technical reasons throughout the book. Now, Firefox is what we call an open source browser. What that means is that it's not fee basis, and the program code is publicly available, which means that anybody can contribute to it. It's the browser referenced throughout the book, and it's available at this website here. A text editor is a basic way to process text, and our word processes are called what you see is what you get, or WYSIWYG. Word processors include many application-specific information in their files, and this is what we talked about a little bit earlier with the text files not being readable by things like Microsoft Word, but a text editor is a very basic way to process text. We talked about this a little bit in the beginning of the course with .txt files. Now, our word processors are what we called what you see is what you get, or WYSIWYG. Now, word processors include many application-specific information in their files, and that's why, like a Word document can't be opened by a text editor, but text documents can be opened by Word. This information will confuse browsers, though, and so we want to use a text editor to write HTML because it's going to be that really basic plain text file. Text editors don't use any kind of that extra information that the word processors do. So browsers will like it because it's written in what we call ASCII, characters only. Now think of ASCII as just the normal keyboard characters with nothing strange added in. Text editors can figure out what language we're writing in, and then they'll add the color to your code to make it easier to read. Operating systems will come with text editors already installed. For instance, TextEdit is found on Macs, and Notepad comes with Windows. However, we are suggesting Text Wrangler and Notepad++ as better programs for writing HTML. So to produce your first HTML page, we're going to follow these instructions. In your text editor, you're going to open a new document. Then you're going to carefully type in your text that's going to be on the next slide. You're going to remove the preliminary material goes here with yet, and you're going to replace the main content of the page with hello world inside of the paragraph tags. Then we're going to save the file as starterpage.html, and then we're going to try opening the file with Firefox browser. So here's what that code looks like. We start our text file out with telling it that we're going to be writing in HTML. Now, this is the standard that is given by the W3 org, which is one of those requirements for configuration and standardization. We have our head tag, our body tag, and our HTML tag is closed down here, which those are our three required tags in all HTML documents. you can see that this code here is going to display in our page as Hello World. The title starter page is going to show up on the tab of the internet browser, and then the text Hello World is going to show up on the web page as the content itself. So when HTML is written, files have to be open in both applications, the text editor to make the changes, and then the browser to see how those changes are displayed. We want to double click on the file to open it with the default application or your browser. Now, Firefox isn't set as your default browser. You may notice that your HTML will open in like Internet Explorer or Chrome instead. That's fine. You'll just be able to see all the differences that the browsers make with the HTML file. So all HTML files have the same structure as the starter page HTML file that we just spoke about. So we can now use this as a template for any kind of future HTML coding. We can set up a new folder to keep our files in, and use the new page as a template will ensure that all the pages have the correct form of that head, HTML, and body tags which are required. So documents can have headings and subheadings, and HTML provides several levels of heading tags. H1 is level 1, H2 level 2, all the way down to a H6. Now headings will display content in a new line, and they're going to be bold, and as they get down from level 1 to level 6, they're going to decrease in size and also decrease in boldness. So when we look at the HTML format versus the display format, the source code is going to tell us how to produce the formatted page based on the meaning of the tag. So it's written in a structured format to make it easier for people to understand. Indenting is frequently used to emphasize the tag's meaning and to also make it more readable for the web designer. Spaces that have been inserted for readability are called whitespace. Now, whitespace is created with spaces, tabs, or new lines by hitting the enter or return key. But HTML will ignore that whitespace, and the browser will turn a sequence of whitespace characters just into a single space. Now, if you want to keep that whitespace, you have to use a tag called pre-formatted. This is going to be the information contained within the pre-tag, and it will be displayed exactly as it appears. The width of a line text is determined by the width of a browser window. So if you minimize that window and change the size of it, it's going to stretch, and the line will break in different places depending on how big that window space is. So here we have an example of what that white space looks like. You can see on the left-hand side here, we have several pieces of white space in our code. Now, because these tags are the ones that really matter in the HTML when it's being read, this white space that we're seeing here isn't going to be read that way when it displays on the web page. You can see that when this HTML is turned into the web page, we don't have any of those breaks or any of that white space here. That's because we can use this white space just to make it more readable when we're reading this code. So if a web page had to show a math relationship, for instance, we're going to use what is called the escape symbol. Now, the browser might misinterpret a paragraph tag if you do the P like that, just as a break. So using the angled brackets as text is prohibited. So to show angle brackets, we have to use an escape symbol. Now, what we want to do is use the abbreviation after that symbol, followed by a semicolon, to show what we mean when we're showing any kind of math headings. Cascading style sheets is one of the best practices of web design today. We also call this CSS, and it's responsible for much of the design of web pages. When we want to set a global style, in other words, something that applies to the entire web page, we want to make sure that we place it in the header information. It will then apply to the whole web page. If we just want it to apply to one line or a particular segment on the web page, we want to place that information inside the pair of style tags. For each tag, we can give it different properties. For instance, in this, we have style, body, background, colors, and this result will result in a background being black and all the text on the page being white. The text between the tag's angle brackets, known as the tag element, is given an element name. So when we style a particular tag, we want to use that name only. We're not allowed to use the brackets here. And after the element name and inside the curly braces is the list of the property or the value pairs separated by semicolons. So you can see that the syntax here is a little bit different than HTML. Now, inline styling is what we talked about a little bit before with that style tag. If we want to make a styling specification that applies just to a tag in one place or onto a certain line of that web page, we want to use the style attribute inside that one tag. For instance, B-style color red. Now, what this will do is that word text will turn red in the actual web page display itself. There's two parts to making hyperlinks. There's the highlighted text in the current document, which is called anchor text, and then there's the address of the other web page, which is the hyperlink reference. Both parts are specified in the anchor tag using attributes. So when we are talking about anchor tags, we want to start with A. We want to make sure that there's a space after the A but not before it, because this stands for anchor. This is going to give the hyperlink a reference, and we're going to use href or hyperlink ref as the file name, so that you have the href equals and then the actual name of the file, to make sure to, and we have to make sure to include the double quotes. Now we'll close that anchor tag with the other angled bracket, and we're going to give the anchor text. So as we've talked about before, we usually use the term marking up when we're talking about HTML. So to turn normal text into what we call a hyperlink, we use what is called anchor tags. Both parts of the hyperlink have to be specified in an anchor tag. We have to begin it with the angled bracket A, and then we also have to have the href attribute, which is the hyperlink reference. You're going to have the href equals and then the file name encapsulated in the double quotes. You're going to want to close that anchor tag with the angled bracket, and you're going to want to make sure that the hyperlink is ended with the /A tag. Here's an example of what that looks like. Here we have Bertrand Russell. Now you can see that the normal text, it's just in black saying Bertrand, and that's here. Now here's where our hyperlink, that anchor, starts with the href, and notice that we always have to have a space in between those two. Then we have the actual URL, or the website address that we want it to link to, and then the text that we want to have activated as that link. So you'll see that now Russell is highlighted and underlined, showing that this is now a clickable hyperlink, and when you click on it, it will take you to this website here. We do the same kind of a thing with image tags. That's going to specify a file that contains some kind of a photograph or an image, usually JPEG, GIF, or PNG. Here what you see is image source, or IMG SRC. We do the same thing with the file name and the double quotations, and then the alt description specifies an alternative form for the image, which is going to be a textual description. This is for those people who have text readers or for who the image won't show. The alt tag was introduced to assist people who are visually impaired, and screen readers don't know what the image is, but they can read the description of the alt tag. So we require all alt tags in our HTML when using images. Then it will also show the alt information, like I said, if it's not available or it loads slow. So the file name needs to be used to correct the file extension. Now you'll see that some browsers will only read GIF and JPEG. The addition of .png files wasn't until 2008, so if you're using a browser that's earlier than that, you'll have to make sure that your images are only GIF or JPEG. The attributes of the image tags, you can specify a width and a height, and you can also specify the size of an image. So here you see that puffer JPEG is going to appear as 200 by 200 pixels, even if the actual size of the photo is much larger. So you can specify only the width or the height, and it will keep it in proportion to whatever the original image was. So here's an example of what that puffer image looks like when we change our different dimensions. You can see the effect of changing the width and the height attributes. So if we keep it as a square, 200 by 200, it's going to show up as an original but smaller thumbnail of the original image. Now if you change it, it'll just squish it down to 200 to 100, or you can do it the other way and squish it horizontally. So we use styling when we're doing our images because you can see the images that are inserted at the page in the point where the tag is or specified in the HTML breaks our text up and makes it really hard to read. So a better way of doing it is to place your image and then wrap your text around the image so that we can read the text around them. We can do this either by imaging or putting the image on the left with the text to the right, or vice versa. And then we make the text flow around the image with the style attribute in the image tag. Now the style attribute that we're going to use is either float left or float right. That's going to apply to the actual image itself, and then any text will show up on the opposite end of the image. Now you don't have to use text as an anchor link. You can also use images to make a hyperlink and link to a new website. You can combine an anchor tag and image. What this looks like is this example here where we have the Ahref history red square. Now you see the image tag comes right after that, and you have the alternate red box to show for people with those visual impairments. Now when the page displays, the usual highlighting that links receive is going to be used to mark the GIF image as a link. We have a term called absolute path names when we're talking about web addresses or URLs. What this is the entire URL, including the HTTP at the very beginning. This is because the web browser needs to know how and where to find the page. So we have to make sure that we have that protocol specification, which is our HTTP, then that actual domain or IP address. In this example, it's the bios.com, and then a path name to the actual file itself. If you remember when we were talking about hierarchies, it'll go to bios.com, and then it will use this path extension to find it. It'll go down into the Sci folder, and then down into the Russell file to actually retrieve that web page. We also have what is called relative path names, and these are links that refer to other web pages that are on the same site. So if I have a site that consists of 5 different web pages, all of those web pages are going to be located in what we call a local root folder. Since those pages all reside in the exact same spot in the same folder, I can make a relative path name to them. I don't have to use the full URL. These pages are going to always be stored in either same or nearby folders or subfolders. And then the anchor tag is going to use a relative path name. That's going to describe how to find the reference file relative to the file in which the anchor tag appears. So when we go deeper into the folder, what that looks like is when you have a file containing the anchor and the reference file, and they're in the same folder, all we have to do is give the file a name. So in this example, the HTML would look like the anchor tag href russellbile.html versus that long HTTP URL when we were using the absolute path name. Now when we reference a file that's deeper or in a subfolder of the directory, we have to give it a path from the current folder down to that file. So in this example, we're saying that you have to go into the biographies folder and then find the russellbile HTML file. We can also go up in our hierarchy. So there's a Unix operating system technique to navigate up to another folder, and that's by adding .. to the beginning of your code. So in this example, it says each .. is going to move up one level higher in the hierarchy. So you can see that if we do a .. it's going to take us from the folder we're in into the next folder up. So we're down in the biographies folder in this example. And if we do a .. it's going to take us up to that root folder. So another example that we can use when we're formatting our HTML is what we call the span attribute. Now that's basically to surround text and provide a place for style and other attribute information. So in this example here, we're showing a span example of a font style, Helvetica, and then a font family of Gothic. Now you can see that it's changing the fonts down here in the actual web page, and that's because of these span styles that are used in our code. We also have list tags. Now the easiest type of a list is what we call an unordered list. What that means is it's just going to be bullet items. So it doesn't really matter what order these list items are put in because they're basically all on the same level, and we do that with this LI tag. The UL stands for unordered list, and it's always going to give you these bullet points. These items are also going to be enclosed within the LI tag. That's your list item. So each item that you want to have in the list has to have that LI tag within the unordered list encapsulations. The other type of list that we use is an ordered list. Now this is the one where it does actually have an order, and it does matter what order these display in. So you have the 1, 2, 3, 4. So you can see that there, instead of the UL, we're using OL for ordered list, but you still have the same list item attribute tags here for each item in your list. The bullets are going to be replaced with numbers, and the ordered list will behave just like the unordered list. We can also do a list within a list. So this is where you get those sub-bullets here. So we have pear, apple, Granny Smith, Fuji, and then cherry. The pear, apple, and cherry, we want to be on the same level. But the Granny Smith and Fuji, since they're both types of apples, we want those to be underneath. So the way that we do that in our code is by creating an unordered list with the list items on this level. And then for this one, we create another unordered list as part of this list item. We also have what is called definitional lists, and that's going to be indicated by the DL tag. They're basically made of definitional terms surrounded by the DT tags, or definitional data surrounded by the DD tags. So you can see an example of that in this code here. So basically it's just putting the Homo sapiens under man here, and then the Homo sapiens under woman here, with the DT and DD tags underneath the DL tag. Tables are very useful in formatting our design, especially when you're making forms for the web. So it's a good way to present information that needs to be formatted in a way. Tables are a nice way to present information, especially if you wanted to have clean formatting and alignment without doing a lot of styling code. So it's like defining a list of lists. What we have here is the main table. And you can see that right now we have a border of 1. That's going to create this little 1 pixel border around all of our cells. Now TR stands for a table row, and then TD, like our list items, are the actual data items that are going to be contained within the table cells. So for each table row, we're going to have the table data, and then the next table row is going to have some more data. We also have to make sure that we're always closing our table tag to encapsulate the entire table example here. The table can have a border if you use the border attribute, but if you delete that out, it's just going to be invisible columns, but it's still going to format this the same way, and each table row is still going to have the same spacing and alignment. So here we have an example of what this looks like in code, and then the representation of what it will look like on the web. Now in this particular example, you can see that we have a caption at the top, and this is going to show up on the web page as basically a title of your table data. Now we have a border of 1, which is causing these lines here. And then we have 3 table rows, but you see this first table row has this bold in it. You can see though that these table items are not actually put into any kind of a bold or EM tag. So we're not styling it that way. Instead, what we're using is the TH tag. What that stands for is table header. So we're telling the HTML that these top 3 cells are the header columns of our table, and it's going to automatically format those as such. We can give tables captions and column headings, and we can use the caption tags to put that title at the very top. Those are always going to be centered at the top of the table. The column headings are always going to be that first row, and again we use the TH for table heading tag to display those in bold. Now let's talk a little bit more about cascading style sheets in the CSS. CSS is going to consider every HTML5 element to be enclosed in a box. Now, even though those boxes aren't going to be visible unless we make them visible, you're going to be able to clearly visualize the content, the padding, the border, and the margin, even without those borders being shown. So when you're talking on a global scale as far as your entire website, at this point we've placed all of our style information in the head tag, which will apply to that entire web page, or directly in the tag, which will only apply to that one line. If we want to easily have the same style information on multiple pages or throughout our site, we have to have a consistent look and feel. We should use a style file. Now all that's doing is taking that CSS code that we normally put in the header tag and putting it into what we call an external style sheet, and saving that style sheet and then linking our pages to it. So when we transfer the style section of our page into the new text file, we don't include any of those style tags, just the style elements. You're also going to want to make sure that you save this with the CSS file extension, not HTML. So for an example in our textbook, they use myfavestyle.css. Then we go back to our original HTML page and we add a link to that CSS page in the header content. The link is going to look something like this, where you have the link and then the style sheet, type is text/CSS, and then the actual file name itself. It's okay to use both a separate file and internal style tags, but there's going to be a hierarchy in such. Now that's the reason that we call it a cascading style sheet, because the style information sources have a hierarchy and they'll override each other depending on where they're placed. Now the default is going to come with your browser. An example of this is the horizontal roll tag. If I create a HR and I open that web page in Internet Explorer, it's going to show as a long, thin gray line. However, if I open it in Chrome, it's going to show as a little bit thicker blue line. So the browser will determine how it displays certain tag attributes. Now, external is what we just spoke about, where we have the styling saved in a simple text file with the .css extension in the same file folder as where we're saving our web pages. We also have the style section. Now, that's going to be defined inside those style tags and applied just to a specific paragraph or a specific sentence to some little piece of content on our web page. We have inherited style, which is a property set by the enclosing tag. And then we have tagged style, which is defined within the style attribute. This list is in precedent order. So what that means is that, for instance, tagged is going to be used over inherited. Style is going to be used over that. So what this means is that if, for instance, I have an external style sheet saying that I want all my font to be Times New Roman, but then in a style section, I take a paragraph and I change it to Arial. That style section attributed to that paragraph is going to override my external style sheet of Times New Roman. So anything, as you go down in this list, it's going to override anything that comes before it. So when we add a class, which is a family of styling specifications with a common name, to our HTML, it's in the style definition in the header tag. And we use this in the HTML code at the site. So this is what class looks like. For the style definition, we append the class name. So in this particular example, we are amending scientist to the tag with a .h2 scientist. So plain H2 tags are going to be styled with those features that apply to all of the H2 tags, and each separate class will give additional styling specifications. So here's an example of what that looks like. Here we have a global style information that is specified in the head of the page. You can see that here's my head tag, it starts, and then my title of my page, I have the style type listed here, and then I have some of that CSS code up here in my header style, okay? Then we have the body and then the content. Well, because we're using the H2 tags and we have defined a certain style for the H2 tags here in the header, the H2 is going to show like such. Now here's an example of what it looks like if you don't do that. So we have H1, H2, and paragraph as specific styles in our header text. Now here we have the H1 and the H2, but you can see because I'm using an inline style here, where I'm telling it to align it left, it's overriding the text align right up here in my header code. That's because of those hierarchies that we just spoke about. There's also properties to change the style of links. The default for your links are always going to be blue and underlined. So you can see that you can actually style the anchor tags by doing these different choices here. So in this case, we're taking our link and we're changing it to a dark violet instead of that normal blue. Now the styles are slightly different from the other tags, and the anchor tag has several different states that can be styled separately. These states are referenced as pseudo classes, and then three main states are linked, hover, and visited. Now link will do the style for an unvisited link. Hover is going to be the style for when the user takes their mouse and cursor and hovers over top of that link. And visited is the style for links that have been visited. In other words, clicked and then it redirects them to that site. If they go back, that link is going to show up in that visited color. Navigation bars are common on the tops of many web pages. They can be either horizontal or vertical, and they're built using unordered lists of links. Basically what it does is it uses this unordered list but turns off the bullets. So we take the list style type and we put it as none, which will take those bullets off. To make a gradient background, what we have to do is first create the gradient image and then save it as a JPEG. We want this JPEG to be narrow but tall enough to cover a long page. Then we use this image as the background image and allow it to be repeated in the X direction, which is going to be a horizontal direction. So you take the body, you describe the background image as the URL and then the actual name of your JPEG that you've created, and then you tell it to repeat on the X axis. So we're talking a little bit in this section about tags for formatting. We've talked about working set of HTML tags giving you the ability to create a web page, an explanation of how the links are marked with anchor tags, the difference between absolute and relative path names, the two most popular image formatting schemes and how to place them in a page, a little bit about CSS and how that uses styles, lists, and tables, and the precision available using classes. So let's talk a little bit about how we locate information on the internet. Here we want to talk a little bit about how web search engines work, how we find information, how to use logical operators, and how to find authoritative information sources, and to decide whether information is truth or fiction. So a search engine is basically a collection of computer programs that will help us to find information on the web. No one organizes the information posted on the web, so it's hard for us to get to what we need to. Search engines look around to find out what's there, and then it organizes it in a way that hopefully gets you to the desired result. So the first step in how a search engine works is a term called crawling. This visits every web page that it can find. The crawler basically has a to-do list that's loaded with a set of pages to start. And when the URL is found while crawling a page, it adds that URL to the to-do list. And then the main work of the crawler is just to build an index. So this is what it looks like as sample entry index for tokens around cat produced by the web crawler. It's going to go out there and it's going to find all these different files, and it's just going to basically index them in its list. Now the index is a list of tokens, or in other words, just words that are associated with the page. The token can be part of the page's title, its description, or some content within the page. There are other ways for tokens to be associated with a page, and for each token the crawler will create a list of URLs associated with that token. The second step is what we call query processing. This is when the user presents those search terms to the processor, and then we have the engine look up the word in the index and return to us what is called a hit list. By creating the index ahead of time, search engines are able to answer these queries very quickly. If we do a multiple words query, all the pages returned should be appropriate for all of the queried words. You can also use the word and in this case, it's going to be associated with all the words. If there's no index entry corresponding to a set, it's going to be a list of the individual words. We have what's called intersecting queries, and that's for multiple words when the processor fetches the index for each of the terms. URLs that are in the list are looked up and compared, and then it intersects the list. They're going to be alphabetized to speed up the processing, and it's easier to notice when the same URL is on multiple lists. Here's an example of that. We have these three different tokens, but you can see that the same one is on each three lists. Well, because of the alphabetization, it's able to find that that's repeated on all three. So to intersect several alphabetized lists, we put an arrow at the start of each token, and then the markers point to the same URL and save it. Now, because all the tokens are associated with this page, the marker is going to move into the next position, whichever URL is the earliest in the alphabet. And then we're going to repeat steps 2 to 3 until some marker reaches the end of the list. When we search for pages, usually what we're looking for is often the first on the hit list or in the top 10. This is because of a term called PageRank. It's the order in which hits are returned to the query, and it's determined by this number. The higher your PageRank, the closer to the top of the list it's going to be. Now, Google pioneered this page ranking as a way to determine which pages are likely to be the most important or the most relevant. Now, it works very similar to a voting system. So if page A links to B, then A's link to B will add to B's importance. So what that means is that pages that are linked to by many other pages will have a higher page ranking and are assumed to be more important. So those links from pages with a high page ranking are also viewed as more important. So PageRank is computed by the crawler, and it'll look at page A, then it'll notice links to page B, and then it'll score 1 for B. Counting the number of links to a page isn't sufficient for a relevant result search, though. So after the crawling is completed, the PageRank computation will factor in other things such as the hit list, highest to lowest, and then it will return a search hit list in that order. So what it looks like is basically what we're looking at here. It'll find pages with words, exact words or phrases, any of these words, none of these words, numbers, language, region, update, site or domain. All of these go into the algorithm to determine what is going to be the most relevant result. If you want to do an advanced search, which is going to get you more relevant data but less results, you can use the AND. This is what we call a logical operator. Basic queries are AND queries, and words must be given have to be associated with the page for a hit. Now, we call this a logical operator because in this example where we have human and powered and flight, it's going to rank all three of those terms equally. It's going to make sure that any page that comes back has all three of those terms, and there's going to be a logical relationship between the words it connects. The search engines are going to treat those words as independent, and they can appear anywhere on the page and in any order, but they must have all three to be a relevant result. If you use quotes, that will mean that you want the exact phrase appeared exactly as given, and this is more than the AND query. We have what we call complex queries, and this is another logical operator, or the word OR. Now this hits on pages that are associated with at least one of the words. So in this example where we have marshmallow or strawberry or chocolate, it only needs to have one or two or perhaps all three of those words to give you a result. So if we have a complex query where we do tigers and not baseball, it's going to be a logical operator where it will specify the words that you don't want associated with the page. The and's included because we want both of these requirements to be true. If you want to combine these logical operators, you can do it like arithmetic. It can be combined and grouped using the parentheses, and Google uses a minus sign as abbreviation for not. So if you do marshmallow or strawberry and sundae, what it's going to do is it's going to look for marshmallow or strawberry first, and then it will add in the word sundae after it runs that search. Many sites will offer the opportunity to perform what they call a site search. This means it's only going to look on the current site or within that root folder. The site search is usually offered on a home page with a search window and a go button. We can also do what is called filtered searches. This is where we're going to use constraints to pinpoint a specific page. We can use these areas on the advanced search to limit our search hits and get more relevant data. They don't necessarily use the page ranking to order the hits, and the use of the advanced search filters can be used to get page ranked hits. Now, research on the web requires some serious consideration and strategies. First of all, we have to select good search terms. The better the words are to include in a query, the more relevant results we're going to get. We need to understand how to use the information that is returned. We need to be able to skim the hit list quickly to find what we want. And then when we find a likely page, we need to locate the desired data on that page. So when selecting search terms, we have to think about how do we find the best words to get the most relevant result. It's going to be basically the sequence of finding precise terms in either an advanced search, a general topic, a descriptive term, adding some words to refine the results, or avoiding over-constraining the results. We can also remove words to get a better list. Now, using Google's advanced search will give you control over the results returned, and we can do complex queries, but advanced search does provide us more control but less results. We can begin with a general topic. Since words have multiple meanings, giving the topic can eliminate most of the conflicting words. Many of the hits can be eliminated, and we can start with a topic word that's going to give us a desired result. We want to choose words that are very descriptive and be picky about what we select. We want to select precise terms and take care in using terms that don't have multiple meanings. We want to refine by adding words. Begin with a first guess search, check the results, check the initial hit list to see what you found, and then see if any of that gives you additional terms to search. This may require several rounds of adding a word to the query search each time. So this is a diagram illustrating how the web search hits are narrowed by adding in those additional terms. Here, each circle represents a website, and the 4 boxes represent words descriptive of the web page. And the 4 searches are based on red words. The burgundy words, fuchsia words, and the purple words will collect the pages into the area of that color. So what we mean by over-constraining is adding more words at one time that work best because interesting pages might be accidentally overlooked. So we have to add a word only if we're sure that the pages we want will have that word present. We want to remove specific words because you can eliminate pages that have certain words that you know need to be excluded. It's basically the opposite of adding a word that will appear on a page. The minus sign is a good way to eliminate the wrong interpretation of a word. So what's displayed with each hit? Well, you get the title, which is the text between the page's title tags on the HTML, and then you get a snippet. This is the information that's a preview of what might be on the page. It's usually a short phrase from the page containing one or more of the searched words. The URL is basically that web address, and it will show it what the link is under the title line. And then you have site links. These are useful links from the site, which are basically shortcuts. They're found algorithmically, and they're not sponsored, so usually no one is paying for them. When we check the hits, it's basically a process of filtering. We want to skim the top level of information and look deeper if it looks promising, but if not, you want to continue skimming down the list. Looking deeper will rank the information. Your title is going to be your first source, and when the title checks out, then you want to look at the snippet. Look at those terms that are shown in bold, and if the context around the occurrence that is given checks out, then you want to look at the URL. If the domain of the site hosting the page is given and it's authoritative, then you want to check that out and then check the page itself. At this point, there's pretty much a good likelihood that the page will include information that you're looking for. So once the page has been found, by going through that process, you want to look and see, is this what I wanted? You want to roll through the page, checking out its main features, look for a date to make sure it's current, and then look at a location of one of the keywords. The goal is to determine whether you want to stay on that page and if you have found the information you want. If you haven't found the information you want to go back to the hit list and refine it in some way. If the site is good, you want to decide how important that information is. And if it's high, you want to cross-check the information with another site, basically to check the credibility. You want to find corroborating information. Don't believe everything you read on the internet. Since no one is in charge of the web, no one really checks to see if the information is correct or accurate. We do have inaccurate information, and the information on the web should always be considered suspect. This is because anybody can post a web page and make random statements or claims, whether they're true, partially true, or completely false. Wikipedia is one of those that comes up in schooling a lot, where people want to go out there and cite it as an authoritative source. However, it's what we call an open source document rated by knowledgeable and community-minded internet users. So what that means is that people like you and me and anyone else are going out there and adding into this knowledge base. Since anyone can contribute, it covers an enormous number of topics, but the information contained in there might not be included in a printed encyclopedia or another authoritative source. The coverage and timeliness make it a really valuable resource to start out with research, and the fact that many people contribute to it is both a weakness and a strength. Because since anyone can add anything to it or edit an entry without control, it starts as a really good point for research, but you also have to always verify the information that you find. Applying good research practices will ensure highly reliable information. So you have to question it and say, does it make sense? Is it believable? Is it consistent? Does it fit with what you already know? And never rely on a single source. You always want to use multiple sources and find that corroborating information. You want to assess the site's authoritativeness, and you want to vary the kinds of resources you use, including offline ones. So what does authoritative mean? It means that we're looking for what experts say. We assume that experts are well informed on the topic and what they say is true because they're supposed to be subject matter experts. But there's no way to verify that what they say is true, so we usually accept that it's the best available information. We want to look for respected sources, and this can be thousands of professional organizations that host trustworthy websites. Individuals are also good sources of information as long as we have some reason to believe them. A primary source is a person who has a direct knowledge of the information, and people who interview primary sources are what's considered a secondary source. They are not as reliable as a primary source because what they say is filtered. People who watch journalists on TV or read newspaper reports are tertiary sources, and they're the 3 levels removed from direct knowledge of the event. So when you're looking for these respected sources, you want to make sure that you're looking for information that's going to be respected, credible, and authoritative. You can see here that basically the way that the diagram works showing our different sources, the people who are removed from the event are not going to have as good a knowledge as the person who actually experienced it. The secondary source doesn't mean that the information is wrong, only that the possibility exists and that there's no guarantee that even the primary source is going to tell the truth. However, you usually get more relevant and accurate information going to the source. The easiest way to get authoritative sources is to go to a site that you know is credible. Many agencies and organizations will publish information that you can depend on, and by going directly, you're ensured that the information is reliable. So when we're looking at our site analysis, think of this. Does the site have broken links? Does it give contact information? Does it have a non-web identity? Is the design simplistic or complex? Are there any recent updates or blog entries? And are there spelling or grammar mistakes? Legitimate sites could have these issues too, but you can do some direct research on the information found there. So in this module, we've learned that we need software and our own intelligence to search the internet effectively, how search engines work, and how we create queries. Filtering and subtracting search terms can remove the extraneous hits, and once we found information, we have to judge whether it's correct by investigating the organization that publishes the page and examining the facts claimed on the page. Always cross-check this information with other sources, especially when the information is important. So now let's get into debugging. The reason indexed searches are so powerful is because the computer will take the time to crawl the data and build the index first. Then it will find the index entries for each word and intersect these lists to find the information for an AND query. Search engines can look at billions of web pages and return an answer in less than a fifth of a second. As you can see here with Google, it only took 0.19 seconds to search over 6.3 million results. Now, descriptive terms are known as hits, and that means that the search term is associated with the page. However, it does not mean that the word is actually on the page. The web page structure will help a lot to identify the descriptive text shown in the search engine. The first one is our title, which we've talked about before in the HTML. That's up in your header item, and it encloses a short phrase describing what the web page is about. Then you have your anchor text, and that's going to be your highlighted link text inside the A tag, and that will describe what the page to it links to. The meta tag is a head section, and it can hold several sentence descriptions of the page. And then you have your alt attributes, which is that image tag that will give that textual description. So the power of an index search is that since all software is written by humans, it's not always perfect. So we have to be aware of some possible mistakes. There could be substitutions such as I for 1 or O for 0, / for backslash, and so forth. You can see that certain fonts can be very confusing, such as the Corbel 0 and the O in O look exactly the same. Another thing that is very important is in path names, you need to respect title case. So in this case, all mine is not the same as the lowercase all mine. We have to also make sure that our passwords are case sensitive. So a principle of computing is that you should expect feedback when you interact with the software. We rely on this feedback to show us busy icons and etc. And by paying attention to the feedback, we can catch errors as we make them. So debugging is a process by which one figures out why something isn't working properly. And debugging relies mostly on logical reasoning, and it's learned through experience. So basically, another word for debugging in this particular context is troubleshooting. Humans do it all the time, but the faults and failures in everyday life usually involve devices that are working systems with either a broken or worn out part. In computer systems, if it's not properly designed and constructed, some part of it can fail. So it's different in IT because we may have entered in the wrong data or the wrong configuration information into a working system, and when it's corrected, the system will work. However, you can't always rely on your users to put in the correct information either. We might have a logical design error, in which case we don't get what we think we should get. And we always need to begin this process by assuming that the system is correct and working and that it was some kind of an input error. So we are almost always part of the problem. We command the computer to do tasks and we input the information. So there's 2 or 3 possible problems with the system. It could either be wrong data, the wrong command, or the system itself could be broken. However, most of the time it's going to be the data or the command that's incorrect. So we don't knowingly make these errors, but the computer is always the one that gets blamed. Sometimes it's both hardware and software errors, but human errors really occur much more often. The computer is unable to debug itself, so we have to bypass these errors and continue to use the system, figure out the workarounds and the ways of dealing with it. So think of it as solving a mystery. We need to ask ourselves questions on Do we need more clues? Are the clues reliable? We need to focus and discover on a solution faster. So the first step in debugging is to try to reproduce the error. Since computers are deterministic, they'll do exactly the same thing every time if given the same input. So we can try to determine whether it's a user error or whether it's a system problem by checking to see if we can reproduce the problem. The next step is to be sure that we know exactly what the problem is. Since the computer can perform a sequence of operations after an error, we must eliminate those first as the focal point of the debugging. We have to determine what the exact problem is first. Then the next step is to check all of the obvious error sources. So what kind of errors are obvious will depend on the problem, but we usually check things like inputs, connections, and links. Then you isolate the problem by dividing the operation into those parts that are working and those that are not. Then we try to figure out where the problem is located, we gather more information if needed, and we limit the number of untested assumptions. We try to eliminate as many possibilities as we can. So as a recap, we want to reproduce, determine exactly what the error is, eliminate the obvious, and then divide the process into things that work and things that don't. Now, when you reach a dead end, you have to reassess your information and figure out where we're making a wrong assumption or conclusion, and then step through the process again. As we work through this process from start to finish, we'll make predictions about what should happen and then verify that the predictions are fulfilled. So here's an example of a debugging case study. We're going to look at a simple page in HTML, and the goal is to get a page that looks like the image on the right-hand side of the screen. Now the working page is over here on the left. On the right we see a not working page from Firefox. You can see that here we're not seeing the image. In the events here we're not getting the table borders as shown on the left. You can see here that we're not getting those hyperlinks that are in the different gold and bronze and silver color codes. So we have to figure out why this is showing up this way. Now look closely at how these all show up in different pages, whether it be Safari or Internet Explorer, Chrome, any of those, they'll all show up in different ways. Some features work on some internet browsers while others do not. So the best way to get started is to study the output closely to see where the errors are, and the goal is to notice what features are right and what are wrong. Note that the 4 browsers we displayed display the buggy page differently. They all show the page, and sometimes it's really difficult to find the bug by comparing it to different browsers because each browser is going to interpret that HTML differently. So let's look at the head section of this particular website. Here we have our HTML information, the head with the title, and then some meta information with the style. And these are all our styles up here. Next is our body section. You can see that we have some of those span classes in here to give the code that color. We have some H references to make the hyperlinks. And as we begin debugging this HTML, the first thing we want to do is reproduce the error. So we want to close the browser and reopen the file. And you can see that there's definitely a problem with the HTML. The next step is to determine the problem exactly. So we want to look at the displayed page, and when there's multiple bugs, let's just pick one to concentrate on first. So let's figure out what the obvious is here. We have this image source of the JJK kind grace JPEG. We have alternate text as the autobiography for JJK. We have a width of 100 and a style floating that image right. Notice this little red slash at the very end. So we want to look at the obvious, eliminate them. So what's the most obvious problem with a missing image? Either the file is not going to be where it should be, so the browser can't find it, and we need to check that that image is in the correct folder, which it is. So we've eliminated that as the problem. Next step is to determine what it is. Look at the display page, and when there's multiple bugs, again, we're going to choose one to concentrate on. So we're going to look at the image and find what the most obvious error could be. Let's talk about misspelling the file name. As we spoke about before, caps are very important when you're talking about a file name, so we need to make sure that these caps are in the file name in the folder. It should match exactly what this says. If the path is messed up, it doesn't mention the pick folder, And after fixing the tag, the image will be there. It's an obvious mistake, but, checking these problems will help us solve it. So the only problem here is that we're missing that pic folder and then telling it to go find this JPEG file in the pic folder. We return to determine the next step and the next bug. So again, determine the exact problem, eliminate the obvious, and then divide up the process. So by dividing up the process, we're going to step through the style section one element at a time. We're going to delete the entire element, save the file, refresh the display, and then see if anything is different. If it is, then we're going to go back, undo the deletion, and restore the file to its original form. By removing these elements, it will restore the other formatting, and then we can find the one that's not working and fix it. So to figure out what is wrong with the element in CSS, we're going to repeat that process, eliminating different parts of the line to see which one is the problem. Another approach with this is to be able to re-enter the text, because occasionally files get a little bit buggy and unprintable characters can be hard to locate. So by retyping it, we can consider each part of the styling again very carefully. Now, if removing that element does restore the other formatting, then we found the element that has stopped the styling and we can fix it. Now, we want to repeat that process, making sure that we're going through and finding each part of the styling. So what we can do is we can use things like the error console. This is going to be a tool on Web Developer, and for instance in Firefox, which is the browser that our book primarily uses, you can go up to the error console and see what errors have accumulated. It will tell you here that there's an error in parsing the value, that there's unknown property, that there's an expected declaration. And what we can do is go through each one of these and find out what's going on. So we've debugged the mistakes in the page by applying the debugging guidelines. Now you can check that the book cover file was in the pic folder, and it was. We checked the spelling in the file but found that the path was left out, so we fixed that. We checked that the end tags were present, and they were, and then we looked at the error console to find out the other weird diagnostics. Now we debugged the mistakes in the page by checking that those closing braces were present and separating the working from failing code. Now when we went through and deleted and checked and undo, we found that the TH had stopped styling. So we checked that TH element and eventually spotted that the opening parentheses was missing, so we fixed that. Now look at the error console again and find the new diagnostics. You can see that the padding isn't working, and we noticed that the unit hadn't been set. So all we needed to do is set that unit, and that fixes that. We also looked up caption align to find its caption side, and we fixed that. Now you checked the wrongly colored text, and you spotted a typo in the end tag, which was making that not work. And then the caption small font specification had a colon typo, so we fixed that. Now, additional common debugging feature is correcting text that isn't actually wrong because of a wrong conjecture. Sometimes you can change the program text from correct, but when you're unlucky, you change it from correct to incorrect. And that means that we had to back out and restore the original. So other errors are different from the errors that you thought you had originally, and that's very common in debugging. Programmers never say that they are down to the very last bug, because what we often find is once we solve one bug, it pops up two more. So we have to ask the system to help, and the most effective technique is to use that error console feature. It can be effective if you better understand the results, but the page source should show the color and font-coded HTML source that will tell you how the browser interprets the page. So one of the most powerful debugging techniques is to find ways for the computer to tell us the meaning of the information it stores or the effects of the commands it executes. And having the computer tell us how it's interpreting our instructions can separate the case in which we give out the right command but mess up expressing it and give out the wrong command. So let's look at another debugging issue. Let's say that our printer isn't outputting and we try to print a document but nothing happens. So we have to figure out how to reproduce the error, understand the problem, and check the obvious causes. So first we check the printer's control panel. We check the paper, the cartridges, the cable connections, the file to be printed, and installation of the print driver. Whether others can print is also going to be an indication of if it's our machine or if it's the printer itself. And whether we can print a different document is going to be an indication of whether it's the file or whether it's the printer. So we need to try to isolate the problem. Because we've printed before, we know that the computer is configured correctly. So we try to print a simple document, but nothing happens. So the next step is to unplug the printer from the computer and try again. If we can locate the printer's driver, we can make sure that it's updated, and we can check the printing monitor to see what files are listed. So if you look at the print queue for your machine, it will show you what tasks are waiting before being processed. The best approach when dealing with printer issues is to cancel or trash out all the jobs in the queue and then restart it. We also want to configure the printer so that it tries to print your files immediately rather than queuing them. And we need to make sure that the computer is connected and then reconnected to the computer. So software can contain bugs, and it crashes, and that's very frustratingly frequent. In this next section, we are going to talk about representing information digitally. Originally, the dictionary definition of digitize is to represent information with numericals 0 through 9. The reason that this is too limited for computing is because we can use almost any symbol. So we can do anything that calls for the use of 10 digits as well as symbols. You can see here that 3 symbol assignments for a telephone keypad. We have numericals, symbols, and then the arrow keys. So one practical advantage of the digits is that they have short names, such as 1, 2, etc. But imagine speaking on your phone number on multiple syllable names, asterisks, exclamation, closing parentheses. IT uses these symbols but have given them shorter names. An exclamation point is bang, and asterisk is star. Another advantage of digits is that the items can be listed in numerical order, and sometimes ordering these items is useful for collating sequences. Now, we need to agree on an ordering for the basic symbols and representing that information by symbols. What this basically means is that the patterns used in computing will come into play when we're having the physical meet the logical world. In the physical world, the most fundamental form of information is either the presence or absence of a physical phenomenon. But from a digital information point of view, the amount of the phenomenon is not as important as long as it's reliably detected, whether there's some information or none, and whether it's present or absent. So in the logical world, concepts of true and false are really important. Logic is going to be the foundation of this reasoning, and it's also the foundation of computing. Since the physical world can implement the logical world by associating true with the presence of a phenomenon and false with its absence. So what we're calling this is the PAND-A representation. It's the name used for 2 fundamental patterns of digital information, which is presence and absence. So P and A is the mnemonic for presence and absence, and A is the key property of P, and A is that phenomenon is either present or not present. The presence or absence can be viewed as true or false, and such a formulation is said to be discrete. That means that it's distinct or separable, so there are really no shades of gray in computing. The P&A encoding has 2 patterns, either present or absent, and this makes it a binary system, which is 1 and 0. There's no law that says on means present or off means absent. You can switch these around as long as there's only 2 variables. The P&A representation is where in a specific space and time there's either presence or absence of the phenomenon which can be set and detected. So P&A is known as a bit. This is a contraction for binary digit, and bit sequences can be interpreted as binary numbers. Then groups of these bits form symbols. So memory is arranged inside of a computer in a very long sequence of bits. The physical phenomenon can be encoded, and this information can be set and detected to be present or absent. There's no limit to the ways that we encode these 2 physical states. So we could do multiple stones of 2 colors per square, multiple white stones, and more than black means 1, and more than black than white means 0, or vice versa. But the 2-bit pattern gives limited resources for digitizing information, since only 2 values can be represented. So 2 patterns must be combined in sequences to create enough symbols to encode the intended information. Since computers use a base 2 to represent numbers, also known as the binary number system, when counting in binary, we're limited to only those zeros and ones. So for instance, you'll see 0, 1, 1, 0, 1, 1, 1, 0, 0, 101, and so on and so forth. Hex digits are short for hexadecimal digits, and they're based on 16 numbers. So since it uses decimal numbers and the first 6 are Latin letters, there needs to be a better way to write the bit sequences, and that's hexadecimal digits. So look at the 32 bits below. This represents a computer instruction. Now, writing so many zeros and ones is tedious and it's very error-prone, but we can convert each group of these above into hexadecimal code. So you take the first 8 and then you convert them. Two of the earliest uses of P&A were to encode numbers and to encode keyboard characters, and representations for sound, images, videos, and other types of information are also very important. So to find the quantity expressed by a decimal number, we put the digit in a place that's multiplied by the place value and the results are added. So for instance, the example of a 1010 base 10 is a digit in the 1 is multiplied by its place and a digit in the 10 is multiplied by its place, and so on and so forth. Binary will work in the same way. The base 2 instead of base 10. So instead of the decimal place values of 1, 10, 100, 1,000, and so on, the binary place values are going to be 1, 2, 4, 8, and 16, and so on. So 10, 10 in binary. We take 1 times 8 plus 0 times 4 plus 1 times 2 plus 0 times 1. The binary number will represent the decimal number 8 plus 2. Here's a binary representation of the decimal number 1010. You can see the binary place values and then the bits of the binary number. We multiply the place bit by place value, and then we add to get a decimal of 1010. So the number of bits determines the number of symbols available for representing the value. In this equation, n is pretty much any number, and it's a bit in sequence which will yield 2n symbols. The more characters we want to encode, the more symbols we will need. So anything like letters, numerals, punctuation, symbols are the minimum needed to digitize English text. But we have things like arithmetic, characters not required in English, punctuation, and business symbols. So how do we represent those? Well, we assign symbols to them. We have 26 uppercase and lowercase letters, 10 numerals, 20 punctuation characters, 10 useful arithmetic characters, and 3 others. So there's 95 symbols in all, and that's enough for English. But to represent 95 distinct symbols, we need 7 bits. Since 6 bits only gives us 64 symbols, we have to go up to 7, which gives us a matter of 128. This is ample for the 95 different characters needed for English, and some additional characters can be represented. So ASCII stands for American Standard Code for Information Interchange. ASCII is widely used on a 7-bit code, and the advantages of it is it's standard. So computer parts built by different manufacturers can be connected because there's a standard among them all. And then programs can create data and store it so that other programs can process it later, and so forth. So when you want to extend ASCII, we can go up to an 8-bit code. IBM decided to do this because that gave them a matter of 256 symbols. And so they could get a larger representation with the leftmost bit set to 0. Now that can handle many languages that are derived from the Latin alphabet. It's solved in 2 different ways. First, you recode the second half of the extended ASCII for the language, and then you use multi-byte Unicode representations. So IBM gave this 8-bit sequence a special name. They call it a byte. It's a standard unit for computer memory. And here is a table just showing how those symbols and the ASCII have coded the information into different representations of the bit code. So what is the advantage of long encodings? Well, we try to be efficient by using the shortest symbol sequence to minimize the amount of memory, but there are some examples of the opposite. In the NATO broadcast alphabet, the code for letters is used purposely and efficiently. It's distinctive when spoken among noise. An alphabet encodes the letters as words, where their symbols, Mike and November, for instance, replace EM and EN. The longer encoding improves the chance that the letters are going to be recognized, and digits keep their usual names except 9, which is known as Niner. So here's the NATO broadcast alphabet. It's designated not to be minimal so that people will understand what you're saying. So when you're spelling out a word, instead of saying ABC, you would say Alpha Bravo Charlie. Barcodes are another representation that use more than the minimum number of bits to encode information. This is because the manufacturer and the product are bit combinations are used for each side. One side's a complement of the other, and the patterns were chosen to appear as different as possible from each other. The different encodings make it possible to recognize whether the code is right side up or upside down. Now, converting the content into binary is only half the problem of representing information. The other half is describing the information properties. We have to look at how it's structured, what it's related to, where it was collected, how it should be displayed, how was it created or captured, and so on. This is what we call metadata. This is the information describing the information. It's the third basic form of data, and it doesn't require its own binary encoding. And the most common way to give metadata is with tags. Think back to Module 4 when we wrote HTML and had those meta tags in our headers. The metadata is separated from the information that it describes. For example, the ASCII representation of letters has been discussed. How do those letters look in Comic Sans font? How are they displayed in metadata? Rather than file with Times New Roman, the file is filled with letters and tags that describe how it should be displayed, and then the metadata can be presented at several different levels. The Oxford English Dictionary is the definitive reference for every English word meaning, etymology, and usage. The printed version of this is 20 volumes, weighs 150 pounds, and fills 4 feet of shelf space. In 1984, the conversion of the OED to the digital form began. Now imagine what you could get with searching on a computer, find the definition for the verb set. Now this is part of many words. You find it in closet, horsetail, settle, and more. So software can help us sort out these words. We have special tags that were developed to handle this structure. For instance, HW is a head word, or a word is being defined. PR handles pronunciation. PH does phonetic notations. PS is parts of speech. HM is a homonym, E surrounds the entire entry, and HG surrounds the head group or all of the information at the start of a definition. With these tags, software can use a simple algorithm to find out what's needed. The tags don't print, so they're invisible to the user, but they're included to specify the structure so that the computer knows what part of the dictionary to use. These structure tags are also useful for formatting, for example, boldface used for head words. And by us knowing the structure, it's possible to generate the formatting information. So why did we settle on the word byte? Well, computer memory is subject to error. An extra bit is added to the memory to help detect these errors. That 9th bit per byte can detect errors using a term called parity. This refers to whether a number is even or odd. So you count the number of ones in the byte. If there's an even number of ones, we set the 9th bit to 0. In all 9-bit groups, they have an even parity. So any single bit error in a group will cause its parity to become odd, and this allows the hardware to detect that an error has occurred, but it can't detect which bit is wrong. So IBM is building a supercomputer called Stretch. They needed a word to quantify the memory between a bit and a word. So that's typically the amount required to represent computer instructions. Currently, a word is 32 bits. So why not BITE instead of BYTE? Well, the I to a Y was done so that someone couldn't accidentally change byte to bit by dropping the E. So we began this module by learning that digitizing doesn't require digits. Any symbol will do. We explored the PNA encoding, the patterns, the bits, the 7-bit ASCII and 8-bit ASCII is the standard. We talked about how documents like the Oxford English Dictionary are digitized, and we talked about the mystery of the Y in byte. So let's talk about representing multimedia digitally. One of the advantages of digital sound is that the form of computing is a representation. This means that it allows us to compress it with a ratio of more than 10 to 1 without really changing the quality of the sound. Another key advantage is that representations can be reproduced exactly. So digital image and video is basically a long sequence of RGB pixels, and the picture is two-dimensional. Now, if the pixels are stretched out one row after another in memory, you're going to get the long sequence of RGB. An example is a 10 by 8 image is scanned at 300 pixels per inch. That's going to be 90,000 pixels. At 3 bytes per pixel, it will take 21.6 megabytes. And sending a picture across the standard line, it could take quite a long time to do that, or almost up to an hour. Whereas a typical monitor has only fewer than 100 pixels per inch, storing the picture at this really high value is a factor of 9 savings immediately. Now, a 100 ppi picture still requires more than 5.5 minutes to send, but if you want to print the picture requiring the resolution again, you're going to want to have that higher image compression. So it means that you're changing the representation in order to fewer bits to store or transmit that information. Faxes are an example of this, where they just encode the page in white or black, and then encode specifying to how long the first sequence should run, and then the next sequence, and then how long the next sequence is, and so on. The run length encoding is called lossless compression scheme. This is the original representation of zeros and ones, and it can be perfectly reconstructed from the compressed version. The opposite of lossless compression is called lossy compression. And this is when the original representation cannot be exactly constructed from the compressed form because for whatever reason those extra pieces were cut out for saving's sake. The MP3 is probably the most famous compression scheme. It's lossy because the high notes can't be recovered. That's because there's no reason to put in the high notes that our ears aren't able to distinguish. JPEG is also a lossy compression for images. It exploits the same kind of human perception characteristics that MP3 does, but only for light and colors. So those colors and lights that aren't in our visual spectrum will be discluded. Humans are quite sensitive to small changes in brightness, which we refer to as luminescence. The brightness levels of a photo have to be preserved between uncompressed and compressed versions because people are not sensitive to small differences in color, which is chrominance. JPEG is capable of a 10 to 1 compression without any kind of detectable loss in clarity simply by keeping the regions very small. Here we have an image of lifesavers on the beach. You can see that in A and B, you really can't distinguish the quality difference between these two, whereas in D, you can obviously see the pixelation. It's possible to experiment with different levels greater than 10 to 1, and the benefit of that is smaller files, which is going to allow a faster download time when you're talking about web pages. But eventually the picture begins to pixelate or get the jaggies, as you can see in the Lifesaver example here in D. MPEG is the same idea applied to motion pictures, and it seems like it would be an easy task, just taking each image or frame and using greater levels of single image compression. But the problem is it takes a lot of stills to make a movie. And in MPEG compression, the JPEG type compression is applied to each frame. It's called interframe coherency. This is 2 consecutive video images, which are usually very similar, and it only has to record and transmit the differences between these 2 frames. That will result in a huge amount of compression. Very sophisticated technology will enable the computer to read these printed characters. This is what's called optical character recognition, or OCR. The business applications that use this are like U.S. Postal Service or banking, and it's basically a scanned image that is basically able to see what those characters are and put it into a readable format. Latency is when the system must operate fast enough and precisely enough to appear natural. It's the time it takes for the information to be delivered, and long latencies make us wait, but it can also ruin the effect. If there's an absolute limit to how fast the information can be transmitted, and that's the speed of light. If you have a long latency time, you're going to get a break in the motion computing, or you're going to get a break in the image, and it's going to discourage the user. Bandwidth is how much information is transmitted per unit of time. The higher the bandwidth, it usually means lower latency. Now, virtual reality is challenged by both latency and bandwidth limitations because by creating that synthetic world and delivering it to our senses, it's a really difficult technical problem to get that quality and that clarity without having the latency. So 4 bytes can represent many kinds of information, and this is a fundamental property of information. It's called the bias-free universal medium principle, where bits can represent all discrete information. They have no inherent meaning. So all discrete information is represented by bits, and discrete things are things that can be separated from each other or represented by bits. Given a bit sequence, there's no way to know what information it represents because the meaning of this comes entirely from the interpretation placed on them by the user or the computer. So computers can represent the information as bits. Bits can be interpreted as binary, and bits do not always represent binary. There's ASCII characters, RGB colors, or an unlimited list of other things. Now this is an illustration of the principle that bits are bits. The same 4 bytes shown can be interpreted very differently. So in summary, the RGB color is an intensity at a 1 byte numeric quantity represented as a binary number. The binary representation and arithmetic are the same for decimal numbers, but they're limited to only 2 digits. The decimal equivalent of a binary number is determined by adding their powers of 2 corresponding to the 1. And we can use arithmetic on the intensities to compute the representation. When digitizing sound, we want to make sure that the precision is a measurement to determine how accurate the digital form is, and uncompressed audio can require more than 80 million bits per minute. Compression makes large files manageable, MP3 for audio, JPEG for still pictures, and MPEG for video. These compact representations work because they remove any unnecessary information. Optical character recognition, or OCR technology, helps us to read things like barcode scanners, banking, and such. The bias-free universal medium principle embodies the magic of computers through the universal bit representations and unbiased coding. So let's talk about the principles of computer operations. Here we're going to talk a little bit about what the software stack are, fetch, execute cycles, and the ALU. We're going to describe the purpose of the operating system and compiler and see how large tasks are performed with simple instructions. Computers are used throughout your day. We're continually using computation. Things such as laptops, cameras, tablets, iPods, desktops, GPS navigators, and TVs are all devices that we use. Now what we have here is a processor. This follows the program's instructions. The operating system is a program that performs common operations and will make your computer a useful device. Software is the programs. Instructions tell the processor what to do, and the fetch-execute cycle will execute the instructions. Memory will store the data, and hardware is the physical parts of the actual computer. When you get a new app, it's a really long sequence of bits, and a team of programmers created the bits but didn't type them one by one. We have software characteristics. For instance, when working in C#, each line only has a few symbols on it, and the English words are blue. Some words can run together, like set and start timer with the parentheses. If we make one small type, the program will have a bug. So we can digitize much more than just letters and numbers. We can also do it to multimedia, which is considered photos, audio, and video. So let's talk about how these are represented on our computer display. Pixels are small points of colored light that are arranged in a grid, and each pixel is formed from 3 colored lights, red, green, and blue. This is known as RGB, and it will always be in that order. As you turn on a light at a time, the display will either turn red, green, or blue. If you turn all of them off, it will be black, and you turn all of them on, it will be white. All other colors are made by using the different amounts or intensities of these 3 lights. Now, by combining the red and green, you will get yellow. Now, most people think, hey, when I combine red and yellow, that makes orange. But there's a difference between colored light and colored paint. The reason for this is because paint actually reflects some light. The white light will strike the paint, and what's absorbed is what we can't see, and what is reflected is what we do see. But in the case of a pixel, the light shines directly at our eyes. Nothing is absorbed or reflected. We just see that pure colored light. So what you can see here is a close-up image of an LCD, which is a liquid crystal display pixel grid. At the left is a standard arrow pointer, and the enlargement in the middle shows the RGB triple lights that make the pixels. Most are at full intensity, creating a white background, and some are turned off to 0 intensity to create the arrow outline. A 2x2 white pixel region is further enlarged to show you what these pixels look like. The intensity of the RGB light is usually given by a binary number stored in a byte. Representing the color of each single pixel requires 3 bytes, or 1 for each color, where the smallest intensity is all zeros and the largest is all ones. Doing the math for Module 7, the range of values is 1 through 255 for each color. Black is the absence of light, so the RGB bit assignment for black is all zeros, whereas white is the full intensity of each color, so the bit assignment for white is going to be all ones. Consider blue, which is all the red is off, all the green is off, and all the blue is on. These 8 bits specified as intensity have the position values. If you want the subpixel at half intensity for each bit, it will contribute half as much power as the bit itself. Now the color intensities can be shown here from the dark blue on the top to the lighter blue on the bottom. Progressively increasing the intensity for a blue subpixel, each bit will contribute half as much power to the bit to the left. So how do these powers of 2 combine to make a decimal number? Well, you can change these colors by addition. To make a lighter color of gray, you can change the common value to be closer to white. Adding 16 to a binary value will lighten that RGB intensity. So imagine that all the color is lighter still by another 16 units of intensity, and it's already filled with a 1. Will you carry that to the next higher place? So same as decimal addition, but only with 2 digits. You work from right to left, adding the digits in each place position, and then writing the sum below. Also, like decimal addition, there are 2 cases. You either add the numbers in a place and where the result is expressed as a single digit, or you add 2 numbers and the result requires carrying to the next higher place. When digital information is changed through computation, it is known as computing on representations. For example, changing the brightness and contrast of a photo. The brightness refers to how close to white the pixels are, and the contrast is the size of difference between the darkest and lightest portions of the image. Photo manipulation software often gives us values of the pixels in a levels graph. This is what a levels graph looks like. 0% is called the black point, or all zeros, whereas 100% is the white point, or in hexadecimal code, FFF, FFF. The midpoint is called the gamma point, and this is the midpoint in the pixel range. If you want all the pixels to be closer to intense white but keep the relative relationships, all you need to do is add 16 to each pixel. So in this case, a pixel which is 197, 197, 197 will become 213 in all 3 values. The goal is not to shift the levels diagram right, but rather to stretch it out toward the right. You need to add amount to each pixel as before, but add a smaller amount for dark pixels and a larger amount for the light ones. So let's look at the new levels graph. The levels graph for the GGGM photo, original and after brightening, and by adding that 16, is just shifted to the right by 16. This is stretching the pixel values from a range of 38 to 239 up to 255. So for every original pixel, you need to subtract the amount of the lower end of the range. That tells how much to increase each pixel position. The smaller is going to be the darker numbers get lightened less than the lighter numbers. Then we multiply by the size of the new interval divided by the size of the old one. So when you add the low end of the original range back in again and return it to each pixel, its new position along the second line. The equation for this value is the new image. Then you round the answer to a whole number. So for the original pixel 239, you should get 255. And for the original pixel 157, you should get 167. Whenever the 3 bytes differ in value, there's going to be color. Highlights are the lightest 25% of the pixels, and shadows are the darkest 25%. And we have to count those pixels to know the values. You want to pick the lowest value and go up to the next level and keep adding until you have approximately a fourth of the total. You want to pick the highest pixel value and go down to the next level, adding until you have the top fourth of the total pixels. Then the levels graph for the image will be the boundaries between the highlights, the mid-range, and the shadows. So a simple algorithm to colorize an image is for each pixel, get the red subpixel and check its range. Then, using the color modifications given above for that portion of the image, adjust the color of each subpixel. So in this case, we're changing the gray to sepia by checking each pixel and deciding if it's a highlight, a mid-range, or shadow, and then replacing that with the corresponding revised RGB assignment. So an object that creates sound by vibrating in a medium such as air is called sound. These vibrations push the air, causing pressure waves to emanate from the object, which in turn vibrate on our eardrums. Vibrations are then transmitted by 3 tiny bones in the fine hairs of our ear, stimulating the nerves that allow us to sense the waves and hear them as sound. The force or the intensity of this push will determine the volume, and the frequency, or the number of waves per second, is the pitch. To digitize, you must convert this to bits. So for a sound wave, we want to use a binary number to record the amount that the wave is above or below the 0 line at any given point on our graph. So since there are infinitely many points along the line and too many to record every position of the wave, we take samples. So we measure at regular intervals, and then the second is called your sampling rate. The faster the rate, the more accurately the wave will be recorded. If the sampling rate is too slow, your sound waves can fit in between the samples and you're going to miss important segments of the sound. So the Nyquist rule says the sampling rate has to be at least twice as fast as the fastest frequency. Because humans can hear sound up to roughly 20,000 hertz, a 40,000 hertz sampling rate will fill this rule for digital audio recordings. And for technical reasons, and a somewhat faster than 2 times sampling rate was chosen for digital audio, so you'll see most digital audio sampled at a rate of 44,100 hertz. Now, the digitizing process when it comes to sound is basically the sound wave goes into the analog. We convert it into the zeros and ones. It goes from digital back into analog and out the speaker. The digitizing process is basically your sound is picked up by a microphone, which we call the transducer. The signal is then fed into the analog to digital converter, which is an ADC, and that takes the continuous wave and samples that at regular intervals, outputting it for each sample a binary number to be written to the memory. Then the process is reversed to play the sound. The numbers are read back from memory into a digital to analog converter, or DAC. Then the electrical wave created by the interpolation between the digital values will fill in, slowly moving from one value to another, and the electrical signal will be input into a speaker, which will convert it to a sound wave. Now the sound is picked up by a microphone. When you get a new application, it is really just a long sequence of bits. A team of programmers created the bits, but didn't type them one by one. So the characteristics of software, such as C#, each line will only have a few symbols on it. The English words are going to be blue, and some words will run together, like set and start timer. If you make one small typo, the program's going to have a bug. Now, software is available in the operating system. Reusing code that's already been developed has lots of advantages. It can reduce your effort, leverage other programmers' knowledge, and updating it is a single instance, which is easier than changing it in a lot of different places. So we have what's called the fetch and execute cycle. This is the instruction execution engine and a machine that cycles through a series of operations. So what the fetch execute cycle consists of is it'll get the next instruction, figure out what to do, gather the data needed to do it, then it will execute it, save the result, and then repeat. This happens billions of times per second. So the 5-step cycle or operations are repeated in a never-ending sequence, and as the name suggests, the operations described in the previous paragraph are instruction fetch, instruction decode, data fetch, instruction execute, and result return. All computers, regardless of their implementing technology, have these 5 basic parts or subsystems: memory, control units, a logic unit called an ALU, an input unit, and an output unit. So this is what that looks like when you're looking at the subsystem. Your inputs are going to be things like your mouse, your keyboard, scanners, printers, And then we have things like hard disk and USB memory. These can be inputs and outputs. Then you have things that are strictly outputs, such as your monitor, speakers, so forth. Now, the principal subsystems of a computer really consist of that memory, ALU, and control unit. So you can see that's why those are color-coded differently. The memory will store both the program while it's running and the data on which the program operates. So there's a couple of properties of memory. First of all, there's discrete locations, which means that the memory is organized as a sequence of discrete pieces on the modern memory. Each location is composed of 1 byte, or 8 bits. So it's going to be a discrete. Memory not only stores the program while it's running and the data on which the program operates, but is organized as a sequence of discrete locations. Keep in mind that each location is comprised of 1 byte, which is 8 bits. Every memory location has what we call an address. This is going to be a whole number starting at the variable of 0. Now, the memory locations record or store values, and there is a finite capacity, meaning that they can't be expandable to any size. There's a limited size to it. So some of your data may not fit in the memory location that has been allocated. Since the memory location is a byte size, you can have this common visualization of computer memory. Look at it as a diagram of the computer memory illustrating its key properties as shown here. The address of the location is displayed above the box, and the contents of the location is shown in the box. You can see that these are discrete locations, and each box holds 1 byte each. If the data that needs to be written to the memory is larger than this 1 byte, it's not going to fit. It can store only 1 ASCII character or a number less than 256. So blocks of 4 bytes are used as a unit so often that they're actually called memory words. Now, random access memory, or RAM, is basically the out-of-date, you may have heard the term RAM. This stands for random access memory, and it's basically the inherent computer memory in the computing system. Random access is actually out of date. It simply means that the computer can refer to the memory locations in any order, and it's measured in either megabytes or gigabytes. Now keep in mind that latest day applications require lots of memory to handle the space required of programs and data. The control unit is where the fetch-execute cycle occurs. In circuitry, the fetches goes out to the instruction from memory and performs the other operations of the fetch-execute cycle on it. A typical machine instruction has the form add 4000, 2000, 2080. Now, it looks like those 3 numbers should be added together, but what it really means is that whatever numbers are stored in memory locations 2000, 2080 be added together, and then the result be stored in location 4000. So here's an illustration of what that single instruction looks like. If you had a single ADD instruction producing different results depending on the contents of the memory from the locations that were referenced at that instruction. So what we're talking about here is the arithmetic logic unit, or the ALU. This is what does the math. It can add those 2 numbers, and then it uses logic gates or simpler circuits to implement operations like AND or OR. Now, there are also circuits for multiplying and comparing 2 numbers, etc., but the ALU will carry out each machine instruction with a separate circuit. Lastly, we have our input and output units, and these 2 components are the wires and the circuits through which the information moves into and out of a computer. Now, a computer without input or output is really useless. The whole point there is to make the inputs and outputs as intuitive as possible. We have things that we call peripherals. Now, this connects to the computer in an input or output port, or I/O port. They provide input or receiving the output, and they're not considered part of the computer. They're only specialized gadgets that encode or decode information between the computer and the physical world. The keyboard is an instance of a peripheral. It encodes our keystrokes into binary form for the computer to understand. The monitor decodes information from the computer's memory and displays it on a screen. The peripherals handle the physical part of this operation. We also have portable memory and hard drives. These are used for both input and output. Since they're storage devices, the hard disk is basically called the alpha peripheral, being the most tightly linked device to the computer. Anything that's going to be outside that is going to be a beta or a delta peripheral. Now, the device drivers have to be there for every peripheral to work correctly, because most of them are what we consider dumb. You might have heard the term dumb terminals or something to that effect. That means that it's not going to work unless it's interfaced correctly with the computing system. They only provide the basic physical translation from the binary signal, and additional information from the computer is needed to make it operate intelligently. So we add the processing by software called a device driver, and that's going to give the peripheral its standard meaning and behavior. So every device needs a device driver. The machine instructions are more primitive than what programmers type. It commands the computer to add the numbers stored in those memory locations of 2000 and 2080, and then stored in the memory location of 4000. This is an indirect reference, which means it's referring to a value by referring to the address in the memory. Now, the computer determines which instruction it should execute next by looking at what's stored in that memory and then using what is known as the program counter, or PC, to keep track of the next instruction. As the computer gets ready to process the next instruction, it assumes that it's going to be the next one in sequence. And because these instructions use 4 bytes of memory, the next instruction should be at the memory address of the PC plus 4, or 4 bytes further along that sequence. But not all instructions are in a strict sequence, so we get what we call branch and jump instructions. This can include a location or a memory address, which is encoded and tells the computer to go there next. So this will change your PC, because instead of the PC just going PC plus 4, the computer is going to have to jump or branch to the specified location to continue execution. So just to summarize, the fetch execute cycle includes instruction fetch, instruction decode, data fetch, operation fetch, and the instruction execution, then result return and store, and then repeat. What we can look at is adding the values in memory locations 428 and 884 to store the result location in 800. And then the instruction fetch, the execution will begin by moving to the instruction and the address given in the PC, in this case 2200, from the memory to the control unit. Then bits of the instruction will be placed into the decoder circuit of the CU. Once the instruction is fetched, the PC can be readied for fetching the next instruction. So this is what it looks like here. It'll take the memory from 2200, which is telling it to add 800, 428, and 884. That'll go up into our control unit where the PC is being told to go fetch 2200. The ALU is set up for this operation. So in instruction decoding, it will find the memory address of the instruction's data, and then they'll operate on the 2 data values that are stored in the memory. So the instructions have the addresses already for those 2 source operands, and these addresses are passed to the circuit that fetches them from the memory during the next step. So the decoder will find the destination address for the result return step and place the address in the RR circuit. Then the decoder will determine what operation the ALU will perform next and set up the next ALU. So what we're seeing here is in the instruction decode, it's going to pull apart that instruction, set up the operation in the ALU, and then compute the source and destination operand addresses. In the data fetch sequence, the values that are operated on are going to be retrieved from memory, and then the bits at the specified memory locations will be copied into the locations in the ALU circuitry. The data values will remain in the memory, and they're not destroyed. So as you see here, you're going to move the operands from the memory into the ALU. In the instruction execution, the addition circuit will add the 2 source operands together to produce their sum. This is going to be held in the ALU circuitry, and this is the actual computation itself. So as you can see here, we're adding the 42 and the 12 to get the 54. Now the return result is going to be the result of the executable into the memory location specified by the destination address. And once the result is stored, the cycle is going to begin all over again. So you can see it takes the 54 and places it back into 800. So there's a lot of simple operations happening all the time. Computers know very few instructions, and the decoder hardware in the controller will recognize, and the ALU will perform only about 100 different instructions with a lot of duplication. There's actually only about 20 different kinds of operations, and everything that computers do must be reduced to some combination of these primitive hardwired instructions. The ADD is representative of the complexity of the computer instructions, and some are slightly simpler, but some are more complex. Computers can achieve success at what they can do with speed, so they show their impressive capabilities by executing many simple instructions per second. However, the more complex you get, the more latency you're going to have. Computers are an instruction execution engine, and since it does one instruction per cycle in principle, the speed of a computer will depend on the number of fetch-execute cycles it can complete per second. We refer to this as the computer clock. So the rate of the fetch-execute cycle is determined, and it's measured in megahertz, or millions, which is a mega of cycles per second in hertz. So 1,000 megahertz clock ticks 1 billion times per second, which is 1 gigahertz. Here we have some standard prefixes showing the International Convention on Scientific Measurements. It's basically to a power of 1,000, except for when the quantity is counted in binary. So 1 cycle per clock tick is a computer with a 1 gigahertz clock. This is going to be 1 billionth of a second, or a nanosecond, between clock ticks to run the fetch-execute cycle. In that amount of time, light travels about 1 foot. So modern computers try to start an instruction on each clock tick. They pass off completing the instruction to the other circuitry, and this process is called pipelining. It frees the fetch unit to start the next instruction before the last one is done. So it's not quite true that 1,000 instructions are executed in 1,000 ticks, because it's already starting as the last one's wrapping up. Here's an example of that in a schematic diagram. You can see that the pipelined fetch-execute cycle on each tick is really starting a new instruction, but it's running, and then as it finishes, it passes along to the data fetch circuit and so on. Now, when the pipeline is filled, only 5 instructions are in the process at once, but 1 instruction is finished on each clock tick, making the computer appear to be running at 1 instruction per tick. Assembly language is a source code where the bits in the processor need an object code, a binary code, or a binary. So before the source code becomes an object code, first it needs to become what we call an assembly code. Primitive programming languages use words instead of zeros and ones, and so to convert that source code into assembly code, the source code has to be compiled. Every programming language has its own compiler. Integrated circuits are a form of miniaturization. This makes the computer clocks run at gigahertz rates because the processor chips are so tiny. The electrical signals can travel 1 foot in a nanosecond, and in early computers, which were the size of whole rooms, they could never have run that fast because the components were too far apart. So making everything smaller has actually made computers faster. Early computers were made from separate parts or discrete components that were wired together by hand. There were 3 wires coming out of each transistor and the 2 wires from each resistor, so that the 2 wires from each capacitor, and so on. So each of these had to be connected to the wires of another transistor, resistor, or capacitor. Now what we have is the integration of these components. And all these components and the wires that connect them are manufactured from similar materials, which is a single multi-step process. Now the technology places the 2 transistors side by side in the silicon, and a wire connecting the 2 is placed in a position. This makes it into a printing process that we call photolithography. Now we begin by depositing a layer of material like aluminum on the silicon. Then we cover that layer with a light-sensitive material called photoresist and place a mask over it. The mask is going to have a pattern that will correspond to the features being constructed, and then they expose it to UV light, which will cause the open areas to harden, and then the unexposed areas will be washed away, leaving that pattern. So hot gas will etch the original layer, and then the remaining photoresist will be removed. The pattern will still remain. So this is what that looks like in the early steps of the fabrication process. And then you can see a blow-up image of the computer chip on the far right-hand side here. So semiconductor technology, it basically just conducts that electricity to control when the semiconductor does and does not conduct the electricity, which is the main process used in computer construction. So the simple principle of setting up a situation in which the conductivity of the wire is controlled to create that logical conclusion. It's basically on is 0, off is 1. So it's the basis of all these instructions and operations of a computer. So in the ALU, the circuit will compute any logical value of X and Y. And such a circuit is part of the ALU performing the instruction execute step of all of these instructions. The field effect is conductivity of a semiconductor, and the objects can be charged either positively or negatively. The effect that a charged object has on each other without actually touching it is called the field effect, and that controls the semiconductors. The ends of the two wires are specially treated to improve their conducting and non-conducting properties, and in part, between the ends is called a channel. Now, because it creates a path for the electricity to travel on, an insulator will cover that channel, and passing over the insulator is a third wire that we call the gate. The silicon in the channel can conduct electricity when it's in a charged field, and charging the gate positively will create a field over the entire channel. Electrons are then attracted from the silicon into the channel, causing it to conduct. And the field is removed, the electrons will disperse into the silicon, and the channel won't conduct. Now, a transistor is the connector between those two wires that can be controlled to allow the charge to flow between these two wires. And it's what we call a metal oxide semiconductor, or MOS transistor. Modern computers are developed with CMOS technology, or complementary MOS. So here's an illustration of what that looks like. The operation of the field effect, you can see the channel and the gate, where the cross-section of the transistor is going to be neutral, and then the region below the gate will not conduct, isolating those wires that are shown in blue. This will charge the gate and cause the channel to conduct, connecting those two wires. So when we want to combine all these ideas, we're talking about a task is performed by the application implemented as a large. Then the program will perform the specific operations of the application, but the program's commands are compiled into many simple assembly language instructions. The assembly language instructions are then translated into a more primitive binary form, and then the fetch execute cycle executes these instructions. So in summary, we've learned that modern software is written in a language using familiar terms and operations, but they're expressed very briefly. The repeating process fetches each instruction as indicated by the PC and then decodes the operation, retrieving the data, performing the operation, and storing the result back into the memory. This process is hardwired into the control subsystem, which is one of the 5 components of a processor. The memory is a very long sequence of bytes, each with an address, and will store the program and the data while the program is running, whereas the ALU will do the actual computing. The input and output units are the interfaces for the peripheral devices connected to the computer, and machine instructions don't refer to the data, but rather indirectly they have different computations which can be done with an instruction by changing the data referenced in the memory location. Programmers use sophisticated program languages to create operating systems as well as complex applications. And the basic idea of integrated circuits are integrating active and connective components, fabrication by photolithography, and controlling the conductivity through the field effect. Now we're going to get into Module 10, which is algorithmic thinking. Here we're going to explain some of the similarities and differences among algorithms and programs. We're going to list 5 essential properties and use the intersect alphabetized list algorithm to do the following. Next, we're going to focus on the social implications of IT. The internet has brought substantial and positive changes to society, and social interactions have been extended well beyond the experiences that we could usually enjoy based on our geography. We're going to focus on a few of the examples that have brought about positive change. Crowdsourcing refers to solving a problem or achieving a goal by combining the contributions of a large, unconstrained volunteer population. Wikipedia is a great example of this, and it's probably one of the most famous crowdsourcing enterprises. The goal is to build a database of all knowledge through a global effort of volunteers. Another example is volunteers that were helping NASA by tagging images from the Mars rovers. Crowdsourcing is a new phenomenon that is made possible by the free and easy communication enabled by the internet. A crowd is obviously important because it increases the number of people working on a project, which is a benefit for people with the problem. This is an example of a cockpit image from the NASA's Be a Martian welcome page. Anybody can log into this, say that they're a Martian citizen and join, and then add into the NASA database for the Mars rover images. By opening up the project to a wide variety of people, the participants have a wide variety of skill sets. They can actually be faster and more efficient at the task than subject matter experts hired to do this job, because their skills and knowledge might lead to a better solution. This is a really good example in Wikipedia, which is proven in most cases. So what's in it for the participants? Well, a lot of the people think that it's fun. They can earn points or win prizes. They receive a sense of satisfaction that they're contributing to something or adding to that project. And many of these projects require skills that are more challenging than, for instance, watching TV. So it gives them more of a sense of accomplishment. Fold It is another example of a game program in which teams compete to fold a protein. And what they do is that they manipulate the proteins to twist them as they float around in cells, and how they fold largely determines how they work. Now, medicine didn't know a protein until it knew how to fold it. So they created this game, put it out to the public, and basically worked on these proteins. Well, what came from that is that they were able to come up with solutions that helped us So one of the most fascinating things is using Fold It. The structure of the protein that's associated with the AIDS virus was solved in 3 weeks. So the Fold It program works on proteins that are really important to AIDS, cancer, and Alzheimer's research. Free Rice is another example of this. It's a vocabulary game, and the player is given an English word and then 4 possible definitions. If you pick the right answer, it will donate 10 grains of rice to your bowl. Kickstarter is also another crowdsourcing social implication where people with creative projects will pitch their ideas. They'll say what they want to do, how much money they need to do it, and why it's important, and then donors can contribute towards their goal. Now, if their goal is achieved, the project will be funded, but otherwise the donors get all their money back. This is what the Kickstarter page looks like. Now, the online world that we live in today is very different in many ways than the world that we grew up in. Our range of interactions is much broader now, and we may never meet face-to-face with people that we interact with online. Families and relatives influence our online behavior very little, is what we're saying. So we can be anonymous on the internet, and no one knows how we behave, but we're not entirely anonymous online. There are means to get the identities of people on the internet, and we all want to enjoy the benefits the internet gives us, so our daily uses of the internet should encourage us to behave. What this leads to is what we call net etiquette. These are the guidelines for proper behavior, and it applies to the social interactions on the internet. It was originally developed for email use, but now it's interpreted more broadly to be civilized behavior in any of the social settings on the internet. Net etiquette guidelines for responsible behavior are listed here. You can see that there are several of them. And the specific guidelines for email is basically following rules of respect and good behavior to meet general business practices. Now, there are additional good behavior habits to adopt as well. For instance, ask only about one topic at a time. If you send out an email message requiring a response, it should only address that one topic, because most of us handle one matter at a time. The reader of a one-topic message can respond to that matter and then delete or archive the mail. But with multiple topics, it's likely that one or more of them is going to either be dropped or ignored. Another thing you want to do is include context. If you include the original message in the reply, it will give a context for your answer so that you can give the short reply without having to leave the receiver clueless. When you're answering, you want to put your reply before the included context. You also want to use automated replies if you're unable to answer your email for a few days. It's polite to set these up when you're on a vacation or saying that you're away to indicate when you can be expected to read your email again and respond. The automated reply is generally available from your mail server, and you will know when you're not, people will then know when you're not responding rather than feeling ignored or snubbed. You also want to answer the backlog of emails in reverse order, because when we keep up with reading our email, we usually answer messages in the order that they're received. But when you haven't, then it's best to answer email in reverse order, because many of the oldest messages are going to have resolved themselves while you are away. Another guideline is clarifying the ownership of email. Most people assume that a sent email is private, and it's impolite and inconsiderate to forward an email without getting the sender's permission. So ask permission to forward an email will give the sender a chance to review the message and decide if there's something in it that shouldn't be passed along. Using emoticons is a way to communicate clearly when you're trying to talk about feelings. Emails and texts are casual writing, and others may misunderstand it if you don't choose the right word. So emoticons are a way of letting us indicate our intent, and they're very familiar. Now, the offensivity perspective can be summarized as follows. So one of the things that we need to be cautious of when we're using IT is what we call the onion. This is based on a humor magazine that was specializing in news satire, and it produces news stories that are almost believable. But what we see is that a lot of people, rather than checking an unbelievable story by asking if it makes sense, or they'll just simply believe it and then repeat it, and it continues to propagate. Another thing to be aware of is suspicious activity. You need to be aware if your software is acting strange or behaving unusually, because this can be an indicator of a software problem such as disk fragmentation or a computer virus infection. If the computer behavior still is acting up after a reboot, you might need some help. Passwords are a key part of our daily interaction with computers, and the point of a password is to limit access to only those who know the sequence of keyboard characters that you have chosen. Now, the computer will store your password as an encrypted file, and it's been recoded to hide the meaning, so the password is transformed into what they call ciphertext that can't easily be read. The ciphertext is saved and then compared. The encryption technique used is called the one-way cipher, and no one knows your password except you. The computer doesn't even know it, it just knows that encrypted version. So to verify that you know it by encrypting what you type in and then comparing those two encrypted versions to keep with your account. If your passwords are lost, they can be recovered. For systems using a one-way cipher, it doesn't work. There are basically two goals when you want to create a quality password. You want to make it easy to remember by picking a topic from which all your passwords are chosen, and you want to make it hard to guess. So you need to compress or scramble or recode the password phrase to be unintelligible to anyone but yourself. So in easy to remember, we can avoid forgetting them by picking a topic that we always use for passwords. Now that will help us remember the password because they're going to be associated in our mind. But when we try to remember your password, you're going to know where to start thinking, but it's not going to be obvious to anybody else. Hard to guess means long passwords, which are harder to guess than short ones. So we want to choose a password that's at least 8 characters long. And you want to include numbers and letters, and if it's allowed, you want to include symbols as well. You want to mix upper and lowercase letters, and you want to avoid any kind of dictionary words. So here's an example. You could begin with the quote, "May the force be with you." If you drop the, you could be, "May force be with you." If you change May to the 5th month to 5, you can get 5 force be with you, and so on and so forth. You can see that there's a lot of different ways to encode this or scramble this that will make sense to you in your mind, but won't be easily decipherable or guessable by somebody else. Here's another example beginning with the title, The Matrix Trilogy. And one that's beginning with the name Hollywood. One strategy is to have 3 passwords to use in a variety of circumstances and then always use one of them. Some of these are like 4-digit numerical passwords for pins that aren't obvious, a 6-letter digit password where there's little risk if compromised, and an 8-digit plus symbol password for cases where a serious risk exists. By using the passwords repeatedly, we won't have a problem remembering them, and if we forget which one we used, there's only going to be 2 other possibilities to try. So chances are that we won't remember. Spam is an unsolicited commercial email. A person can be sent more than 100 spam messages per day, and there's laws against it in many places, and spammers are prosecuted, but it still persists. Spam filters can separate legitimate mail from spam, but in most cases your ISP will already have that spam filter installed. Now, how well that filter processes the email messages as they arrive, separating them, is a variable feat. Determining if the email is spam is really just a programmer's best guess. But the program will scan the email and then assign a score to it that will measure how many properties of typical spam are also in that email. Then if the score is above a certain threshold, the email will be considered spam. Users can check the spam quarantine to make sure that no legitimate mail is being stopped. Now, after a spam filter scores the email, it's delivered to your inbox if the score is below that threshold, but some mistakes are inevitable. So setting the threshold will allow you to control how to handle those close calls. The lower threshold, saying a message is spam, is based on fewer properties, whereas the higher threshold is going to be based on more properties. So this is how the spam threshold affects email delivery. You can see here that fewer legitimate messages are quarantined, more spam gets through your inbox, and more legitimate messages quarantined, less spam gets through to the inbox. There's also a plethora of scams on the internet. One of the most famous ones is what we call the Nigerian window scam, and it's so common that it's actually referenced in pop culture. It's also known as an advance fee fraud or as 419 fraud. Now what this was is that someone you've never heard of claims to have great wealth that they can't access, and they ask you to help in transferring the money out of their country. And for your help, you're going to receive a large share of the money. They emphasize that the operation is confidential, and after you agree to help, then amazingly things go wrong with the transfer. So what they do is they say that they need some money to like bribe officials or pay various fees before they can get the money. And then after you agree to help, they say more money is needed before they can get the money because something went wrong. So you keep giving them the money thinking that you're going to get much more in the future, and this is the advance fee part of this scam. So the scammers need more and more money as time passes, and eventually you threaten them and then they disappear. So this is what one of those Nigerian window scam emails looks like. And unfortunately, it's been extremely successful. The U.S. Secret Service claims the Americans have lost tens of millions of dollars every year to this scam. And in a recent variation, the email says that you've won a lottery in another country like the UK. This is what the Euro Millions announcement looks like, and it's also an extremely successful scam. They say that advance fee fraud, that you're going to have to pay the lawyer a consultation fee or something before you can get your lottery winnings. Phishing is a social engineering process of convincing trusted people to give up personal data voluntarily. And the reason that we call it phishing is because it's an acronym for password harvesting phishing. The spam email is sent out designed to look like it comes from a reputable organization, and then the mail will use actual content from the organization's site. So the message will make use of several claims on behalf of the organization. It will either tell you that your account has been accessed by unauthorized people, that you're owed money, that there's been a security breach that they're trying to fix, or they're performing an audit and trying to find possible problems with your account. they'll ask you to log into a website to resolve the issue, and most of those links will connect to bogus sites that will look like the reputable site. So you can protect yourself from phishing by opening attachments only when you know who sent them and why. You should only give information online when you have initiated the transaction yourself. And before entering any information, think about how you got to that company. Pay attention to the domain name of the company as well and make sure that it looks legitimate. Here's an example of a fraudulent email phishing attempt that claimed to be from the IRS. Now, protecting your intellectual property is information that is something that can be owned but is the result of a creative process. Now, the act of creation will give the creator ownership of the result, and in the U.S. and most of the world. But sometimes there are multiple forms of ownership. For instance, on her tour, Katy Perry sings a song written by Paul Simon. He owns the words and the music, but she owns the performance. So if a person creates something while working for a company, generally the company will own that information. All such human creations are called intellectual property, and the two aspects that we're interested in are software and copyright on the web. So when you buy software, you actually didn't buy the software itself. You're basically leasing it. So you have the right to use the software, but the ownership will still remain with the company that marketed it. So the agreement will allow you to use it on at least one computer, and it may permit you to use it on all the computers that you as an individual own, but you can only use one instance at a time. By installing several instances for convenience, it may be okay, but you have to check the terms to see if the software vendor will allow that. You can't sell it or give it away legally because you don't own the commercial software. If you do, you can violate the terms of the contract that you agree to when you open the software package, and unless the programmer gives you the explicit right to copy and distribute the software, you legally cannot sell it or give it away. Now, a version of software that's tried before you buy is called shareware. Now, this is usually distributed over the internet, and the idea here is that you can try it out, and if you like it and use it, then you pay the person who created it. But it's basically an honor-based system. So if you use the software, you should pay for it, and they consider it unethical to download software on the implied promise of paying for it if you use it and then never following through. There's also what we call open source software. So software from vendors is what we call proprietary, where the vendors keep the source code private. And then software for which the program is publicly available is known as open source software. Now, open source seems not to make sense because it's, who's paying for the technology and how can a company make money if the product is publicly available for free? Well, companies developing this technology make their products open source to promote wide distribution, and then the money is made selling specialized versions to corporate clients or providing customer support and selling other software. Advocates of open source point out that if the software is publicly available, then other people will work on it and improve it, making a better product and then making it worth more. Copyright on the web is the second issue that we're concerned with. So when a person writes a term paper, builds a web page, or creates a sculpture, they automatically own the copyright on that work in the U.S. and most nations of the world. It's the creator's copyright unless the creation is work for hire, and in that case, the owner is the person who paid the creator. So what rights are included on a copyright? Well, it protects the owner's right to make a copy of the work, use work as a basis for new work, distribute or publish the work, publicly perform the work, and publicly display the work. So if you're looking at copyright on the web, there's no application or approval required. The work doesn't require the copyright symbol, and it's copyrighted the moment it's finished, whether you have that symbol or not. Now, you might be tempted to bypass copyright law by restating a work in your own words, but if your creation is too much like the original, you've produced what is considered a derivative work rather than new intellectual property. There's some that's called free personal use, and just because someone else owns it doesn't mean that you can't use it and enjoy it. You are free to read, view, or listen to it. You can even print it and save it as long as it's for your personal enjoyment. So when permission is needed, you need to look at, Do you want to make a copy, use the work as a basis for a new work, distribute or publish it, or publicly perform it? If any of those are true, you must get permission from the owner. We also have what's called the concept of fair use. This is the gray area in which limited use of copyrighted materials is allowed without getting permission from the owner. It's recognized in copyright law to allow the use of material for like educational or scholarly purposes, and also to allow limited quotation of copyrighted works for review or criticism, to permit parody and a few other uses. So it's considered fair use when you look at the intent and the plan of the use. What's the nature of the work in which the material is going to be used, how much of it's going to be used, and what effect this would have on the market for the work if it were widespread. So the Creative Commons has copying and distribution allows. Creative Commons is the last type of copyright that we'll cover, and in this, creators keep the copyright to the work, but they license it for the general good. What this means is that you can tag your work with the license link, and it allows copying, distributing, and performing. Attribution is what most Creative Commons licenses have, and that gives credit to the creator, but creators can waive any of the rights that they keep for themselves. So in summary, we've talked about expecting the unexpected as a useful survival skill. The challenge here is to think about the unexpected event and then to try to correctly determine whether and how to respond. Spam, scams, and phishing are everyday occurrences, but with skepticism, we can't avoid trouble. Creating an easy-to-remember password is emphasized by selecting passwords that are connected to a common topic, and it's smart to choose simple passwords when little security is needed and choose more obscure, complicated passwords when there's a greater risk. There's different characteristics of copyright. When we create intellectual property, we immediately have the copyright to it. And when others hold the copyright, we may be restricted on how we can use it. Asking permission is always the safest thing to do. And the Creative Commons license provides a simple way to create and share intellectual property within the existing laws, and it promotes creative communities. Next, we're going to cover privacy and digital security. In this module, we're going to talk a little bit about the meaning of privacy. We're going to explain the meaning of the OECD Fair Information Practices, the issues concerning U.S. privacy, and we're going to list the ways computers can be compromised. You're going to understand public key crypto systems and a simple encryption from clear text to ciphertext and perform the reverse. So when we're speaking about privacy, what you need to keep in mind is that buying a product is going to generate a transaction which will produce information. Now, if you pay with cash, generally that ensures your anonymity. When you pay by check, credit card, or debit card, or if you pay through mail order or the internet, you're giving the computer information that it can store and then reuse. By providing a preferred customer number, they're able to match your purchases to what you purchase and your registration number. And then buying a product that must be registered for a service agreement or warranty also captures all of your data and information into a warehouse where they can then resell that information. So you think about the different way that these information on simple transactions can be used. Now, obviously, this is a normal part of conducting business, and such as keeping a check record until it clears. But the information at that point then technically belongs to the store. So if the store decides to base on your previous purchases to send you ads for other items, the store is then using the information for the standard business practice of generating more business. Now, if the store sells your name to others, then information has gone in to generate more business, but can it be considered misuse? Well, it depends on how the information is going to be used. In the past, it was hard for people's privacy to be violated without their knowledge, but now with the modern technological devices, people's privacy is easily violated without them even knowing about it. So your image and your information deserve sufficient safeguards against improper circulation. So we tried to control the use of this information, and what it comes down to is figuring out who controls the use, if any, of this transaction information that's collected on us. There's four main possibilities. First of all, there's no use, where the information should be deleted as soon as the store is finished with it. You have approval or opt-in, where the store can use it for other purposes, but only if you approve. Then there's objection or opt-out. This is where the store can use it for other purposes, but not if you object. And then there's no limits, which it means the information can be used in any way that the store chooses. There's also a fifth possibility called internal use, and this is when the store uses the information to conduct business with you, for instance, keeping your address, but not for any other use. It wouldn't include giving or selling your information to another person or business, but it may not require your approval either. So if the transaction took place outside the U.S., we have laws and standards that would place it between 1 and 2 on the spectrum, but closer to 1. And if the transaction occurred in the U.S., the laws and standards place it between 3 and 4 on the spectrum, but closer to 4. Many Americans assume that there's a privacy law that is close to the fifth case, which is internal use. However, the actual definition is the right of people to choose freely under what circumstances and to what extent they will reveal themselves, their attitude, and their behavior to others. So it's really difficult to define, and generally, privacy concerns 4 aspects of our lives: our bodies, our territory, our personal information, and our communication. So this definition emphasizes first that it's the person who decides the circumstances and the extent, and not anyone else. Second, it emphasizes that the range of features over which the person controls the information embodies every aspect of their person. However, sometimes we want publicity and sometimes we don't, and strong privacy laws ensure that we control the dissemination of our information. But there are threats to this privacy. Basically, government, business, and snooping or gossiping private parties will be handled by security. Historically, the governmental threat of spying on its citizens worries the people the most. The business threat is a more recent worry, and there's 2 types of business threats: either surveillance of employees or the use of business-related information for other purposes. Now, we have what's called voluntary disclosure. And in principle, this means that the person can enjoy perfect privacy by simply deciding not to reveal anything to anyone. But it may be in our best interest to reveal private information freely in exchange for some real benefits. So, for instance, doctors can receive our personal information so that they can help us stay healthy. Credit card companies get our personal information to track our credit record in exchange for the convenience of paying with a credit card. And employers read our email at work because we're using the employer's computer to do a job. The government may have information on us regarding our parents' names, birthplaces, race, ethnicity, etc., for the purpose of enjoying the rights of citizenship. So when we reveal so much about ourselves, our attitude, and our behavior, how private can we really be? Well, the people or organizations that give or sell the information to anyone else are also revealing information about us. And in this term, our privacy is compromised. But there has to be clear guidelines adopted for handling this private information. And one of those guidelines is called the Fair Information Practices Principle. In 1980, the Organization for Economic Cooperation and Development, or the OECD, developed an 8-point list of privacy principles that became known as the Fair Information Practices. They've become widely accepted as a standard. The public has an interest in these principles becoming law because they give businesses and governments basically a guideline where they have to do due diligence to protect citizens' rights for privacy, thereby protecting themselves from any kind of criticism or legal action. An important aspect of these principles is the concept that the data controller or the person that's setting the policies has to interact with the individuals about their information and has to be accountable for those policies and those actions. So the standard 8-point list of privacy principles consists of limited collection, quality, purpose, the use limitation, security, openness, participation, and accountability. So here's a description of what each of these mean. In the limited collection, this is basically placing limits on how much they can collect. The purpose is really looking at the intent of what they're going to do and then limiting the purposes of that intent. The quality means that it has to be accurate, complete, and up to date. The use limitation means that they can't use it other than any way stated in the purpose principle except with the consent of the individual. Security means that they have to take measures to protect your information and to protect against risks of disclosure, unauthorized access, misuse, modification, destruction, or loss. Openness is basically making it possible that there's a general openness of the policies and practices and that you're aware of the kind of information that they're collecting and then the way that they're using it. Participation means that an individual should be able to determine if somebody has information about you and then discover what it is. If the request is denied, then the individual should be allowed to challenge that denial. And accountability means that the data controller has to be accountable for complying with all of these principles. So privacy is not enjoyed much in the world. It often comes in conflict with the goals of businesses and governments. So for an example, the United States hasn't adopted the OECD principles, and this is because U.S. companies profit by buying and using information in ways that are inconsistent with these principles. But the European Union issued a benchmark law incorporating the principles, and the EU directive requires that data about any EU citizens has to be protected by these standards of law, even when it leaves their country. Other countries that have adopted it include Australia, Canada, Hong Kong, and New Zealand. So U.S. businesses and government gathers data contrary to the OECD rules, and the Patriot Act makes it a crime to say that data gathering is taking place. But almost every store and company you do business with has information about you. If you want to know what they're doing with that information, you must read their privacy policies, and often it says we use the information however we like. So one of the big controversies and something that most people are aware with is the Target scandal that came out where big data was compromised by the credit card holders and all of this credit card information was released. Well, big data is that statistical analysis of huge information archives, and the retailer Target can figure out, for instance, if a woman is pregnant from her buying habits. They were able to develop a pregnancy prediction score by analyzing all of the data and then gathering this and finding out the trends and the common themes throughout this statistical analysis. However, the problem is that all this data is also there to be targeted and used by people who have unauthorized access. In June of 2013, Edward Snowden revealed that the U.S. government was collecting complete metadata records from telephone carriers, and the government was also collecting online activity from Facebook, Microsoft, and Google. Included in the data was calls to other countries that have OECD laws in place. Now, in terms of tracking, we're talking about electronic privacy. And tracking is used in two different ways. There's online tracking, which is website automatically sends details about your visit to other content providers. And then there's cell phone tracking, which is positioning information used to map your physical location. In online tracking, we assume it's used to target advertising and marketing organizations, but really anyone could arrange to follow your click streams. HTTP does have a do not track flag that will tell web servers your tracking preferences, but it's up to the web server to honor your request. So we have a couple of browsers that have do not track settings. In Firefox, it's under privacy preferences. In Internet Explorer, it's under tools, safety, and tracking. And in Safari, it's under preferences. Now notice that Google Chrome browser does not support user requests not to track. So do not track is really controversial because consumer behavior is very valuable to marketers, but people don't want anything following them around, even when it's online. So there's two additional protections you can take. One is called the National Advertising Initiative Opt-out Program, and one is called a Do Not Track Me, and that offers a free blocker as well. Now, one of the ways that they put into place this Do Not Track is through what we call private browsing. This is a client-side facility, meaning that it's going to be on the user's computer. And it only concerns the information stored locally on your machine, not what's stored on their servers. So things like cookies, cached files, and history are going to be deleted at the end of the session. And this can be useful when using a public computer. Now, in cell phones, it's possible to determine where the cell phone is even if your location services or your GPS is turned off, because it's based on the proximity to cell phone towers. Now, the Freedom of Information Act was launched in 2010, and companies will keep this information for a while, but the NSA keeps it permanently. So here's basically tables showing the different subscriber information and telling what their call records are as far as how long they use the cell towers, how long they keep your text messages, and the content, how long they keep your pictures, what the IP sessions are, any kind of bill copies, payment history, store surveillance videos, and service applications. Now, when we talk about cookies, that's basically a standard computer concept originally used by Netscape engineers to connect the identity of a client across a series of independent client-server events. What this allows for is for the user to be able to get information more quickly because it saves some of that information so it doesn't have to go back out, retrieve it, and reload it. So imagine that this is your bank server and you're a client. The server is helping a lot of different clients at once, and to know who's who, the server stores a cookie of the information that uniquely identifies you. The cookies are exchanged between the client and the server on each transmission of the information, allowing the server to know which of the many clients is sending the information. Many sites use cookies even when the interaction is not intended to be as secure as a bank transaction. Things like the National Air and Space Museum sent the above. The meaning of the fields is really unimportant, but the first is the server, and the last is the unique information identifying the session. Cookies can be abused. There's a loophole called the third-party cookie, and this is when a cookie is exchanged between the client and the server, which is usually private, but if the website includes ads on its page, the server can direct it to link to the ad company and deliver this ad to you. This relationship places a cookie on your computer. Now, all browsers allow users to control how cookies are processed. You can turn them off, forcing the browser to ask you every time whether you're going to accept it. But turning off cookies will prevent you from being able to do things such as bank online. So you have to set your browser's cookie policy to your own comfort level. This is an example of what that looks like. You can see that we have accepting third-party cookies until they expire, the exceptions, and you can show cookies as well. Now, the security principle of the Fair Information Practices states that those who hold private information are obligated to maintain its privacy against unauthorized access and other hazards such as identity theft. However, Americans do not enjoy protection from this principle. So, identity theft is the crime of posing as someone else for fraudulent purposes, and over 800 identity thefts have been reported from one instance of private information viewed by unauthorized people. Computer security is a topic that is in the news almost daily. So we have a lot of do's and don'ts for online behavior. And when we check with the sender before opening an attachment that we're unsure about or falling for phishing emails, you can make sure that that digital security is in place. However, it really falls back onto the user. There are risks, things such as mischief, which means infecting a computer, causing a nuisance, erasing files, or trashing files. There's information theft, which is stealing your personal information. There's spying, which is they can record videos of you, log your keystrokes, or compromise the secure online activities. And there's resource theft, which is actually taking over your computer. There's a couple of terms and jargon in this particular area. The first one we're going to cover is called malware. This is software that harms computers. A virus is a shared program that contains code to reproduce itself. A worm is a program that is often embedded in an email attachment, and it reproduces itself and sends a copy to everyone on your contact list. An exploit is when a software takes advantage of bugs in the commercial software, and a Trojan is malicious programs that perform unauthorized activities. So what does malware do? Well, it exploits what's called backdoors, and this is software that creates an access path, allowing attackers to run any program they want on your computer. Now, Trojans are also considered as a subtopic of malware, and they can record every key you type, basically trying to find your passwords, extort money, or watch for banking and credit card information. And then rootkits infect your computer and then fight back against security systems. So there's certain things that you can do to protect yourself against these type of malicious activities. First of all, you want to turn your Bluetooth off when it's not in use. You want to keep your phone and other computers password locked. You don't want to automatically click on email attachments, and never enter sensitive information in a pop-up window. So think of getting something for nothing. You know where you're going, and you know when to be skeptical. So you need to use extreme care when you are visiting notorious sites. If something bad does happen, the first thing you want to do is turn off your computer, and then use a different computer to do a web search about what happened. Use an external source for the operating system to reboot. Some plans of action here are to run modern software, install updates often, install an antivirus, set your Wi-Fi router to a security level of at least WPA2, and password protect your phones and computers with appropriate passwords. Know your knowledge and be wise. Now, encryption is information that is recorded to hide its true meaning. A major component of encryption is the key, and they come in two forms, public and private. The key is a magic number that's used to transform text into gibberish or ciphertext, and both the sender and the receiver must agree on the key. The process of sending an encrypted message is a 5-step algorithm. It basically starts with the sender breaking the message into groups of letters. Then you multiply each group of letters times the key. You send the product or the result from the multiplications to the receiver. The receiver then divides the products by the key to recreate the groups and assembles the groups into the message. This works because the math works, and the reversibility of encryption makes them two-way ciphers. So only the sender and the receiver know the key, making the products useless numbers. This is considered secure communication, and this technique just explained is called private key encryption or symmetric. Now here's an example of how that private key encryption works. Now, crypto system schematic diagrams are basically showing the point where the ciphertext goes into the sender and then out to the receiver and then is regathered into clear text. Now, by using a key known only to them, the sender can encrypt this information and the receiver will decrypt it to recover the clear text. In the middle is where the content is exposed and can be snooped, but it's going to be unintelligible gibberish at that point. So real encryption systems actually use much longer blocks and larger keys. The multiplication and the division are not the only operations that can be used for encryption. All that is needed for operation to have an inverse is to divide. Now, the private key encryption works very well, but there is a small problem with it. It is that the sender and the receiver have to agree on the key, which means that they need to communicate somehow. Usually they meet face-to-face. They can't email because they don't have a key yet. So to avoid that face-to-face meeting, what we have to do is publish the key. This is where we get into using public key encryption, and it's two special prime numbers multiplied together. After the receiver publishes the special key, the following will happen. The sender will break up the message into blocks as before. It cubes each block and divides it by k, keeping only the remainders, and then the remainders are transmitted. The receiver will raise each remainder to a higher power determined by the prime number known only to them. Then they'll divide by k and save the remainders, which are the original blocks, and then reassemble the message. So k is the magic public key, but it's just two prime numbers multiplied together. So is it possible to figure out those two numbers from the published key? Well, in theory, yes, but this process is called factoring, and it's tough if the numbers are large. Usually they're about 60 digits apiece, so it's really impractical to factor them no matter how powerful the computer. Redundancy is very, very good. We need to take precautions with our technology, and Business archives files daily and then stores these backups off-site, but we don't usually have that kind of system in place for our personal files. We need to make sure that we have a system recovery to clean up after any kind of a disaster or to find those files if we have multiple computers performing the same work. That way, if one fails, another is up and running. This is what's known as a fault recovery program. We have two different options here. You can do a full backup, which is a complete copy of everything written on the system as of a certain date and time, or you have a partial backup, which is the changes since the last full or partial backup were saved. Changes means they'll just keep a file of any files or folders that have been created or modified, which makes it much faster and much smaller file size. So after a disaster disaster, you can recover by installing the last full backup copy, and then you can make the changes saved in the partial backups in order. So to continue with each partial backup until the most recent, and then you're as close to a full recovery as possible. So when you're backing up your personal computer, you need to make sure that you have a place to keep the copy and you have software to make the copy. The two easiest places to keep the copy are on an external hard drive or in the cloud. There's several cloud companies, and they store the information for you and take the responsibility of keeping it available to you. You don't have to back up things that are like information that can be recreated from some permanent source, any information that was saved but hasn't changed, or any information that you really don't care that much about. If you do need to recover deleted information, you can use file restoration. Backups can save evidence of crimes or inappropriate behavior in businesses, and 2 copies of emails are produced immediately when the send button is clicked. One will go into your sent mail directory and one somewhere else. So this is very useful when you're trying to put together what happened in an event or for business cases. So in summary, we talked a little bit about how revealing personal information can be beneficial, but it can also be abused. The guidelines that conflict with the interests of business and government. The do not track flag, the best way to manage your privacy. The 2 key features of encryption, the invincibility of the RSA scheme, the viruses and worms, and how you can implement a plan of action to ensure that your personal computers remain private and secure.